Welcome to Talkin Science. Today we're diving into the recent discovery of a pulsar by the Murchison Wide Field Array in Western Australia. Nick Swainston made the discovery while processing the data it had collected. We'll talk about that on today's show.
On Apple Podcasts, Spotify, Google Podcasts and YouTube for over 550 episodes. This is Talkin Science.
And Nick, thanks for a little bit of your time on today's show.
You're very welcome. I'm happy to be here.
First up, let's start with the basics. What is a pulsar?
So a pulsar is born when a star dies, which is called a supernova. It's a massive explosion. And we're left behind what's called a neutron star or a pulsar. So that's extremely dense. So in 20 kilometers, it weighs as much as about 1.5 times the mass of the sun. So to put that in perspective, if you had a teaspoon, that would weigh 10 million tons. So it's this really dense, it's really strong magnetic field. It's this crazy thing that we can't really recreate on Earth. So there's these really interesting things that we can study with radio telescopes. So I find them really interesting.
That is very cool. And they can be used as measuring tools, as I understand it, testing the laws of physics under extreme conditions.
Yeah, exactly. So because they're so dense, if we get two of them in an orbit, that's called a pulsar binary, then we can really accurately measure how gravity works at these extreme densities. We can investigate the interstellar medium, like in between us and the pulsar. And there's even these things called pulsar timing arrays, which we're hoping to use to measure low-frequency gravitational waves, but we're not quite there yet.
Well, this discovery that you've made is a big deal in a few ways, but not least of which that it's the first time the MWA has found a pulsar. Now, this hopefully is a sign of things to come with its successor, the Square Kilometre Array, recently passing milestones to get constructing. Do these big telescope arrays make pulsar hunting easier?
Yes, normally. So with the MWA, so like you mentioned in your intro, we've only done 1% of the data, so hopefully we'll find a lot more in the near future. And then the SKA is going to be a huge undertaking. It's a multi-billion-dollar project, and we're hoping once it's complete and we finished our survey, we can triple the number of pulsars that we've already detected, so it should be great.
Well, yeah, you say that 1% of data collected for the pulsar survey. I guess this bodes well for many more discoveries when the operation kicks into main gear with the Square Kilometre Array and all those other big telescopes and focusing in on that data to find more of these pulsars. What does that mean, finding more pulsars? What can that mean for us in terms of studying them?
So every single pulsar we discover is always a little bit different. It's always unique in its own ways. It's different mass, different magnetic fields, and sort of emits a bit differently. So the pulsar I found is perhaps in the pulsar world a bit normal. It rotates about once every second. But it's not just individual pulsars anymore. We need thousands of them to start studying them in larger scales, to start working out models of how they work, and we need lots and lots of pulsars for that. So the more we get, the closer we are to understanding them, hopefully.
Now, one of the biggest things that fascinates me when I read about these discoveries is just how they're done. You interpret a whole heap of raw data, graphs, numbers, and other stuff. Now, aside from practice, how do you make heads or tails of all of that to pick out an object like this pulsar?
Yeah, well, it's very time consuming. So just to discover this first pulsar, I had to use 90,000 CPU and GPU hours on a supercomputer.
Wow.
So to put that into scale, like if you just had a really nice computer at home, that'd take about 2 years to process, but it's a lot faster on a supercomputer. And it spits out thousands and hundreds of thousands of these sort of candidate images where it gives you as much information as possible. And you have to look at it and think, okay, is this real or is this noise or sort of maybe like a satellite that kind of looks like a pulsar? So yeah, it's a lot of work to get through, but it's getting easier now that we're sort of automating as much as we can.
So that automation that kicks in, that really does, I guess, the hard work for you, and it sort of gives you some candidates, as you say. So it spits out some options for you, and I guess you've got to go in there and double check everything and see whether there are things of note in the data samples that it's given you.
Yeah, exactly. So there's actually a bit of machine learning that we put first. So machine learning will do its best and it sort of takes out like 90% of the candidates, and then we're left with the last 10%. But we're hoping to get that better. We have actually a few undergrad students working on improving our machine learning. So hopefully that'll be like 99% we don't have to look at. We kind of look at the best 1%, which will really speed things up. But yeah, I recently even convinced some third-year students to help me look through all these, because I think we have 100,000 in the can at the moment. So there could be more pulsars. We just haven't had the time to, find and follow up and discover. So yeah, a lot of work.
Nick, when you started your PhD work, did you know that there was going to be this much data analysis, or were you hoping for something a bit more exciting? Or is this exciting for you?
It is exciting for me. I'm a glutton for punishment when it comes to software development and processing. I really enjoy just having these big pipelines that take up all the queue and making them as fast as I can. I find that really satisfying. So I was glad to have such a big data project.
And I guess at the end of the day, finding a pulsar and knowing that that this little thing that you discovered in the data can lead to some pretty big things and hopefully some advancements as well in understanding these pulsars, I guess that's a good feeling as well.
Oh, yeah, definitely. So it's now known around a little pulsar group as Nick's pulsar, so that feels pretty good.
Yeah, that's awesome. And it will forever be known as Nick's pulsar. So that is awesome. And hopefully more pulsars to be discovered as you analyze some more data. Have you got anything else on the horizon at the moment? Is there any other data sets that you're looking at?
Oh, we're always processing data and we're always making candidates. So yeah, watch this space. There should be more pulsars soon.
Awesome, Nick. Well, thanks for beaming in. And as I say, hopefully you'll find many more of these pulsars as you keep looking.
Sweet. Thanks for having me.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favorite podcast app 5 days a week. Just search for Trekzone and subscribe.
Welcome to Talkin Science Interviews. Matt Miller with you in studio for today. Wrapping up the very successful 11th Australian Space Forum. Mr. Michael Davies is here with me to chat about that on the other side of the open.
On Apple Podcasts, Spotify, Google Podcasts, and YouTube for over 550 episodes. This is Talkin Science.
Michael, thanks for a little bit of your time on this Easter weekend here at Trekzone. I really appreciate it.
My pleasure.
Now, can you tell us a little bit about the Australian Space Forum, the 11th one now, bigger and better in 2021?
Well, that's right. It started 5 years ago. We've done it twice a year since 2016. It was an initiative of the South Australian government, and it was specifically inspired by the fact that South Australia and Adelaide was due to host the International Astronautical Congress in 2017. So it was a lead up to the IAC and a way of bringing together the fairly disparate Australian space community at the time. And so we started, I recall the first forum had about 50 participants, and it's grown to about 100. The other significant thing about the latest forum was that the Andy Thomas Space Foundation, and I'm the chair of the board of that foundation, we were appointed by the South government to take over the running of the forum recently. So this was our first attempt to run the forum in our own name. And fortunately, in spite of all the risks associated with any live event these days, it was very successful.
It was incredible, and I was really hoping to get down there. I had my press credentials ready to go. Unfortunately, being in Brisbane with what happened over the last week, everything was locked down, and I was locked out of the conference. But watching it virtually was absolutely fantastic. And I think part of what everyone has to do now, holding a live event, holding a conference, add that virtual component in, so anyone can beam in and catch up on these events. Some fantastic panels, some amazing booths around the place from what I saw. With the Australian space industry, the space agency, having been formed now, has that changed the way the forum operates and its sort of goals?
Yes, we are very close to the Australian Space Agency. We see ourselves as supporting what they call their Inspire pillar. That is that space is for everyone, and it has the potential to inspire, especially young people, to think about careers in STEM related fields, and perhaps even one day working in some space role. So the short answer is yes. We try to we work closely with the agency in preparing the content of the forum. We always have speakers from the space agency, and they give us a lot of advice on topics and experts to invite.
And some pretty cool openings at this year's forum this week. The Space Discovery Centre in Adelaide, Lot 14, really developing and pushing forward. Mission Control from Sabre Astronautics also opening as well. Some great news coming out. Southern Launch with their Kunuba test range, or their launch range now. So plenty of excitement to be happening, and plenty more for the Space Forum to sink its teeth into. Are we going to see another one this year, or will it be next year?
This year, yes. In 6 months' time, we're looking at September, and fingers crossed, it will be available both, face to face and online. And yeah, I agree with you. The online component of any conference these days is very, very important, and it also allows people who can't travel, obviously, to ask questions, participate, and one of my jobs was to moderate the questions, and it was fantastic to see so many intelligent questions coming in from the online audience. So it's that will always be a big part of the event, I'm sure.
Well, fingers crossed in 6 months' time, Brisbane doesn't have another lockdown, and I can get down to Adelaide and catch the 12th Australian Space Forum. Michael, thanks for a little bit of your time this Easter weekend. Really looking forward to it. Congratulations on the Space Forum that was just held, and we'll catch you for the 12th one in September.
Thanks very much, Matt.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favorite podcast app 5 days a week. Just search for Trekzone and subscribe.
Welcome to Talkin Science, where we dive into the latest news from space and science. Lloyd Damp, the CEO of Southern Launch, is here to discuss their recent approval to construct the Whalers Way Launch Complex. Lloyd, thanks for your time.
Pleasure, Matt. Anytime.
Well, before we get into it, a quick reminder that you can get behind-the-scenes goss and early access to all the Trekzone podcasts by becoming a member today. Click the join button on any Trekzone video, go to the Trekzone/support, or put your phone up to the QR code on screen throughout the show. Lloyd, first up, can you tell us where Whalers Way is and why it's so important to Southern Launch?
Sure. So Whalers Way is at the tip of the Eyre Peninsula. Now, for those of you who don't know where the Eyre Peninsula is, it is the big peninsula here in South Australia. So it's about half an hour's flight west of Adelaide. And why it's so important to us is when Southern Launch started to look at the business model of launching satellites into space, we identified that the growing market is in the polar and sun-synchronous orbits. So those are the orbits that go around the north and the south poles of the Earth while the Earth spins on its axis. Now, And to do that safely and to do that cost effectively, we needed a location that satisfied a lot of criteria. And lo and behold, it was the Eyre Peninsula here, west of Adelaide, that satisfied the criteria the best. So hence why we're doing the things there.
And you mentioned the polar orbits. Is that one of the key reasons that makes it different from the other launch complex at Cuniba?
With Cuniba, it's about suborbital launches. So the rockets go up, out into space. They deploy a telescope or a camera or test a bit of equipment before then falling back to Earth under a parachute. And the key thing being Cuniba is out across the deserts. You can go out there and actually collect your telescope after the event and inspect it or download the information from it. Whalers Way is all about getting the rocket up into space and then accelerating it to 11.2 kilometers per second so that it stays in orbit around the Earth. So that's the fundamental big difference between the two launch sites.
Now, this approval that you've received from the South Australian Commission Assessment Panel is quite strict. Can you run us through what you're allowed to do?
Sure. So the whole goal of this approval is to undertake up to 3 rocket launches from Whalers Way. This is to help us understand the noise and the vibration caused during a rocket launch and feed that into our major project, so our environmental impact statement. So, as I said, we can do 3 rocket launches. We can build infrastructure, temporary rocket launch pads. We can bring in shipping containers and generators and the likes. At the end of the 3 launches, we have to be prepared to tear out any infrastructure. So, everything that we're doing is removable. In other words, so we can bring in a backhoe, pick up the launch pad and take it off site if need be.
Now, it took 8 months to come to this point. Were there any hurdles along the way?
Besides this being the first time a civilian rocket launch pad has been properly constructed in South Australia, everyone had to learn how to go through the process, and there's a lot of explaining and diagrams and whiteboards and the likes. But the good thing is that everyone very quickly understood what it is we're trying to achieve and wanted to help us, follow the process. And ultimately, getting approvals is up to us, and being able to provide sufficient information to the different authorities. But everyone was very keen to work with us to understand that process because it's never been done before. So.
Is having those conditions on the permit prohibitive in any way?
We don't believe so. And, the company has a very strong environmental ethos through everything that we do. So our, one of the conditions is that we put together an operational and an environmental management plan. We had one of those anyway. So all we've done is dusted that off, so to speak, and handed it across to the regulators. And they've gone, so far so good. So it's none of them have been anywhere or onerous or restrictive in our operations. So.
It is absolutely incredible. So as you say, there are 3 launches permitted with this permit. I'm guessing that the next step then will be to understand what these tests show you and then go to a more permanent facility. Is that how it's going to work?
Yeah, so the next step for us is to get, so I should add, what the state government has approved is only the construction of the concrete and the intended use of the land. We've now got to get approvals from the Australian Space Agency to operate what we're calling Pad 1. So that's been an ongoing process with the agency. And then following that, we then can work to get a launch permit from the Australian Space Agency. So the key thing for us is to be able to link that all through together so that ultimately we can do these 3 launches safely out into the Great Australian Bight.
Well, the regulatory process with the Space Agency, as you say, is the next step. Is there a timeline for when that might come through?
No, but we're working very closely with Enrico Palermo and his broader space agency team. It's fantastic dialogue that we have with the agency, because like the construction of the pad, and sorry, I'm looking towards Whalers Way down that way. This hasn't been done before, so we've got a very, very good dialogue with them as we go through this regulatory process. And we're very lucky in that we've been able to replicate a lot of the policies and procedures from our Kaniba test range across to Whalers Way. And so in doing that, we've started with the base that we know the Australian Space Agency expects and understands, and able to then modify it across to Whalers Way, which is a different environment, different operational conditions, but it's helped us hopefully expedite those approvals. So.
Well, in the press release a little earlier, you mentioned that this is a huge milestone for Australia's sovereign space capabilities. Why is it so important for us to have facilities like this? And why should we be launching into space or even into suborbital planes?
Yeah, so it all comes down to a sovereign capability, right? And more than just a sovereign capability, it provides a new industry for Australia and a new source of STEM, I'll say, inspiration to the future generations. So from a sovereignty perspective, we now have control of one of the most critical domains out there. You know, our mobile phones, our banking, radio won't work without access to space resources. GPS, for example, it's all based on satellites up in space. Should Australia no longer have access to the American GPS satellites, we will need to be able to replenish those or create our own capability. And so this is where it then feeds into the next phase, which is gaining access to that multi-billion-dollar industry, which is space and access to space. A really good example is, you know, Australia is at the very forefront on developing the next generation of atomic clocks. Right, these are incredibly accurate clocks. So for an example, should we lose access to one source of GPS satellites, we, Australia, could partner with other nations developing our own replacement, and then not have to rely on a third-party country to then actually get those satellites into space. So it's a very good sovereign capability, plus then the ability to capture part of that market. And lastly, you know, the space technology truly excites generations of students. We work very closely with quite a few schools, both here in South Australia and more abroad. And you can see the kids light up when we bring out one of the small dart rockets that we launched out at Kaniba last year in September. And we say, this is a rocket, this is part of a rocket that we intend to send to space, right? And you can just see the kids going, wow, I've touched a space rocket, I've seen a space rocket. And so I'm really looking forward to the day when we can say, and this is what an orbital rocket looks like. You know, we've actually got one in Australia. So you know, I see that this complete spectrum of opportunities for the nation moving forward. So, yeah.
Well, Lloyd, I cannot wait for launches from Whalers Way. In person, hopefully, if COVID stays away long enough. Thanks for beaming in today, and good luck.
No, thanks so much, Matt. Anytime.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favorite podcast app 5 days a week. Just search for Trekzone and subscribe.
Welcome to Talkin Science, where we dive into the latest news from space and science. The University of Queensland's Professor Warwick Bowen has led a team that's developed a quantum microscope that can reveal biological structures at resolutions previously beyond our capability. Professor, thanks for your time.
My pleasure.
Well, before we get into it, a quick reminder that you can get behind-the-scenes goss and early access to all Trekzone podcasts by becoming a member today. Click the join button on any Trekzone video on YouTube, go to the Trekzone/support, or put your phone up to the QR code that is on screen throughout the show. Now, Professor, it's not like traditional microscopes at this stage, the ones where we get to look in them and look down at a plate. It's currently spread out all on a table like we can see here in this overlay. Will it ever get to a point where it'll resemble more like a traditional microscope like the ones behind you?
It's not so far away from the state-of-the-art and precision microscopes now. So the kind of microscopes that you use to see down to the nanoscale or see very, very faint details inside cells, they involve these sorts of bright lasers that we're using, and often they'll be on a table much like the ones you see here. They're not like a microscope you see in school, but they're very powerful, useful microscopes. The big challenge really for us is that quantum entangled light is quite fragile, and you have to be careful when you use it. And that introduces a whole another set of requirements that quantum physicists like myself know how to handle and to deal with. But to make the microscope useful for biologists, we have to make that quantum entanglement user-friendly and robust. So that's really a major challenge for the broad usability of these sorts of microscopes.
Well, can you tell us how this microscope works?
Our microscope is a special sort of microscope that fingerprints the molecules in a cell. These microscopes require very high intensities of light, around 1 billion times brighter than the intensity of the sun at the Earth. What we have done is reduce the noise floor of the microscope using quantum entangled photons. That allows us to extract more information, to get better clarity with the same intensity of light, and therefore avoid damaging the sample we're looking at.
What will this breakthrough mean for the scientific community?
I think it will be quite significant. This is a form of quantum technology, and quantum technologies are thought to offer revolutionary capabilities for future technologies and future applications in many different areas. Our microscope is the first sensor that uses quantum entangled light that shows that you can get an absolute performance advantage over other techniques. So that's a major step in this process towards really getting quantum technologies out and into applications.
One of the keys to this breakthrough was to climb over the hard barrier of traditional light-based microscopy. What is the tradition and how did you break it?
You know, microscopy started with the discovery that if you take a couple of lenses and put them in the right sort of order, you can see stuff with more precision at small scales. And that led to the discovery of cells and bacteria and viruses, and basically life as we know it. It completely revolutionized our understanding of our bodies and of living systems. In the 1960s, there was a second massive discovery, and that was the laser. And that led to extremely bright laser microscopes that were awarded the Nobel Prize in 2014 and pushed resolution down into the nanoscale and pushed sensitivity up so we could really see the rich dynamics of biological systems in ways we could never see before. But those microscopes have now hit this major barrier, and that barrier is, in order to get better performance, you need to turn light intensity up. But to turn light intensity up, you start to damage the cell. Basically, you cause sunburn. You give it a radiation dose, and it won't survive. You can't measure it anymore. So what we did was break that particular barrier. We showed that quantum light allows you to extract more information per photon you use in the measurement, and therefore allows you to see more with more clarity and more structures in biological samples than is otherwise possible.
This new microscope provides 35% improved clarity without destroying the cell. Now, I never realized that that was a factor. What does this mean for future studies?
That's a very good question. So it absolutely is a factor, and people worry greatly about the effect of the light they use to probe biological samples on the health and viability of those samples. It's not just destroying them. In our case, the laser, in some cases, would just drill a hole through the sample. right? People use lasers for laser machining of metals, so it's not so surprising. But even before that, you start to create free oxygen radicals that change the health of the cell. You start to change how it behaves, its viability, its function. So people really worry about this. Now, as you say, we demonstrated a 35% improvement in clarity. So we showed that with a given amount of phototoxicity, with a given amount of laser irradiation, we could improve the clarity of images by 35%. That's something. It's not an enormous amount. Really, to see big applications, we're going to need to improve that. And there are ways to do that. The kind of quantum light source that we demonstrated in other contexts has been shown to allow up to a factor of 30 improvement in noise floor, which means that we could improve clarity by a factor of 30 rather than a factor of 35%. In other words, 30 times compared to 1.35 times.
Well, Professor, where did the idea of a quantum entangled microscope come from?
That's a great question. So, in fact, this is a problem. This is a solution that's been understood for more than 40 years. So people in my field, in quantum optics, have known that you could use entangled light, you could use correlations between photons of light to improve measurements in biology. And it had been thought that this would be one of the major areas of impact of this sort of light. But it took a very long time to go from the fundamental theory of the field to demonstrating proof of principle experiments on a lab table with basic, physical objects like mirrors and things like this, to actually being able to use these sources of quantum light in biology. So really, the transition has been this transition from understanding to proof of principles in physics to applications in biology, which just takes a long time. So the idea's been around for a while, and at the same time as this idea had, I'm going to pause for a second. So this idea has been around for some time, and it's really been an idea that's been biding its time, because laser microscopes have also been developing. And so it took until they reached their fundamental limits before it really made sense to apply quantum correlations to improve them.
Now, Wayne, while you lead the team, you're not the whole team. Can you tell us about who is helping to make this quantum microscope a reality?
Yeah, that's right. So this was an effort that was 4 or 5 years of work, and really the major result of a PhD student in my lab, now Dr. Cacere Casasio. So she started her project with this particular result in mind. It was a huge mountain to climb. We didn't know if we'd get up it. So really full credit to her and the rest of the team for making this happen.
Well, what's it like to watch her grow from being your student to earning her doctorate, all while making this microscope a reality?
It's really incredibly rewarding. I think this result has opened the door for her to, who knows where she'll go, but it's opened the door to so many opportunities, and I'm just looking forward to seeing where that leads her and what exciting new stuff she does.
Professor, thanks for beaming into Trekzone.
Very much my pleasure.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favorite podcast app 5 days a week. Just search for Trekzone and subscribe.
Welcome to Talkin Science, where we dive into the latest news from space and science. Macquarie University's Dr. Christian Schwab is here to discuss a new type of spectrometer that will aid in the discovery of exoplanets. Christian, thanks for your time.
Thanks very much for having me.
This is a Trekzone conversation. And you can get exclusive behind-the-scenes info and first play access to all Trekzone podcasts by becoming a member today. Click join on every Trekzone video on YouTube. Go to the trek.zone/support or scan the QR code on screen throughout the show. Now, it's back to you, Matt.
Well, thank you very much, Ross. And a quick reminder too that we are across social media. Search for Trekzone on Twitter, Facebook, Instagram, YouTube, and your favourite podcast feed, and like, follow, and subscribe to us. Leave comments and ratings. That'll help convince the algorithms we're worth promoting. Christian, let's talk spectrometers. And as I understand it, precision is key when it comes to scanning for exoplanets in particular.
Yes, it is. The name of the game is getting the highest precision spectrograph right now to really find Earth-like exoplanets. So unlike other fields of astronomy, in exoplanets, we really search for the one really interesting one. Right, in galaxies, we are at the point where we have thousands of them and people do statistics with them. But in exoplanets, we are really looking for that one elusive Earth 2.0 that is really like our own home planet, and getting to measure that one requires extreme precision from the instruments we build.
So the more precise we get, the smaller the planet we can discover. Is that why our discoveries are skewed slightly to gas giant exoplanets at the moment?
Yes, that's exactly right. So in the beginning, people thought that exoplanets, or Jupiter-like exoplanets, hot Jupiters even, may be very abundant because that's what we found all the time. But this is really a detection effect coming from the fact that we can find them more easily. They produce a much larger signal. So if we use spectrometers to find exoplanets, the technology we use is really, or the technique we use is called the Doppler technique. We don't see the light of the planet itself. We see the light of the star. And what we detect is changes in the spectrum of the star caused by the planet pulling the star around. That wobble causes the spectral lines to shift slightly back and forth. And if you think about the strength of the effect, Jupiter produces a pulling effect, a wobble around the sun of something like on the order 20 meters per second. But the Earth only produces an effect of 9 centimeters per second, so much, much smaller. And while 9 centimeters per second don't sound like a very small speed to measure, so it's often compared to, that's about the speed of a turtle. What we measure it with is light. And so you have to compare those 9 centimeters per second to the speed of light at 300,000 kilometers per second. And the net result is that the fractional change, the minute shifts in spectrum are really on level of a part in a billion. That makes those spectrometers so hard to build.
Now, the NUID spectrometer you've helped developers recently passed its final NASA review and is fully operational at the Kitt Peak National Observatory in Arizona, as we're seeing here. It's an 81 megapixel detector spanning across the light spectrum to detect wobbles on stars, which are the key indicators of planet transits. Can you tell us how all that works to a trained eye, of course?
So what we do is we observe the same target stars over and over and over again. We spread their light with the spectrometer over a large detector. It's like the physical size is like this, 9 by 9 centimeters, many, many pixels. So we record the spectrum in very high detail. And by looking over and over again, we see if the spectrum changes over the course of what we expect an exoplanet orbit to be. So if you want to find something like Earth, then it takes Earth a year to revolve around the sun. So you really want to look over and over again over the course of a year, or ideally more than that. And so we have a list of stars that have been pre-screened, so we know they don't behave oddly. They have the right stability and spectra themselves that you can look for planets around them. And now we just started looking over and over again, any clear night that we have the spectrometer for the next 5 years, in the hope that an Earth-like exoplanet will pop up.
Now, a small-scale copy has been installed at the Macquarie University Observatory. Now, while it's not as powerful, it will enable students to undertake some practical training. What sizes of exoplanets can be viewed at Macquarie University?
It depends on how the code development goes the next few months. Now in lockdown, probably our grad students have a bit more time to code. But really, the precision we could get here, I hope, will be in the few meters per second range, maybe about 5 meters per second. So things like hot Jupiters, or indeed, for example, the very first planets that have been found with this technique, including the one around 51 Pegasi that got the Nobel Prize awarded a few years ago, should be easily observable from here. The spectrograph is really a half-size copy of NUIT. And what's interesting there is it's much cheaper, because we didn't have a particular precision goal, right? We wanted this as a teaching tool, and it's really interesting, at least it was very interesting for me to see just how much cost we can cut if we don't try to get to the very highest stability. So for the real deal, for NUIT, we had a large team of people that really came together, that turned every screw around, really tried to make sure that there's nothing in that whole instrument that can somehow break our stability goal. Here, we will get what we get. And this factor 10 in the bottom, like going from a few meters per second to sub-meter per second, is really the difference between putting it together with a few people or having a team of 30 people working 3 years.
NUIT now forms the blueprint for future spectrometers. What's it like to know this design will be used well into the future?
It's very exciting to have found that particular solution to the problem, right? And so I led the optics design for NUIT when I was a postdoc still in the United States. And so what we really did is we looked at the problem from the top. We said, okay, like let's start new, let's start fresh, let's have a really good look at what is really needed in particular to make spectrographs stable. And so the design that I arrived at was the simplest we could find, because the fewer lenses you have in there, the fewer lenses can be misaligned over time. So we really developed something that has the fewest lenses of any spectrograph of that size in the business, is as simple as we can make it, to be able to make it as stable as we can make it. And it seems to work. We just passed the review, as you said. We deliver about 0.3 meters per second on sky. That's about the best in the world. It's very, very satisfying to see, after years of truly being worried that it may not work, that it actually does work. And now we have that design developed, and we're very, welcoming to other people working with us if they want to build something similar. And of course, things have been published. So this is now a design that's out in the open, and that has been verified. And it's great if it gets, propagated, and we move it further to even better precision in the future.
And the materials used to create these spectrometers, is it tricky to get a hold of the materials? I'm guessing it has to sort of be of a particular quality to be able to get to this point of being ultra precise.
Yeah, we looked at this quite a bit. In the end, we decided to make all the mounts, all the spectrograph mechanics of a particular type of aluminium. A common type, we buy very high grade of that common type, but we make everything out of the same metal to not have changes between the thermal expansion rate between, let's say, a mount that holds a lens and another mount that holds a mirror, and then the bench itself. So going to aluminium really helped us to keep the cost at least somewhat in check. It's nice, the machine, and it thermalizes very well, has high thermal conductivity. For the lenses, things were a bit more tricky. The lenses in that instrument are about 270 millimeters diameter. So we don't use particularly uncommon glasses. That goes back to, let's keep it as simple as we can, but you can't buy them in that size. And so our large prism had to be custom melted for us. All our lenses, the material was custom melted for us in that size. It took a long while, and then you end up with that large lens block, and you really hope you don't break it. So in particular, the prism, which was, the block was some 400 millimeters on the side. And that one got lifted into the spectrograph. No one wanted to really do it. It was just, okay, let's just put it down very, very carefully, very carefully. And it's a beautiful piece of glass. You have that big thing. It's completely transparent. It's made from lead crystal, like your wine glasses at home, which, as you probably know, break easily. And so, yeah, it was an interesting thing, and we were glad that we got this block at all. It was a Japanese company who made it for us.
So I guess there were a lot of sighs of relief in the room when it was finally put into position. No more fine adjustments needed. Being able to see that and then see it actually working and working well must have been a very good feeling as well.
Yeah, it was great. I mean, seeing the first spectrum at all come out of the instrument, so that you can literally, if you take the big detector off and you put a white piece of paper there, you see the spectrum. It just projected, and it's all these beautiful colors, and these are prime colors, right? Most colors we see in real life are not prime colors. They're something reflects and is subtracted, but these are really pure colors, and it looks, if you designed this and you see it come to life after those big lenses have been ordered and everything has been put in, and you see it in real life, it was great. And having it then on the mountain was even better.
Now, I know you said that the small-scale copy there at Macquarie University is not of the same quality, but are you still striving for that effort as well? Have as best of a replica as you can of NUID?
Yeah, the optics design is actually very similar. It's just exactly half the size. And if we go half the size, all the glass materials all of a sudden are off the shelf. You can just buy them. Our workshops here made all the aluminium mounts, again, half-size copy. So the optics and the mechanics are really very similar. But what we don't have is an enclosure that holds the temperature very well. So NUID is in an enclosure, which is in an enclosure, which is in an enclosure, which is in vacuum, which is in an outer kind of meat locker type room, which is in another bigger room that's temperature stabilized. And all these things have thousands of temperature controllers all over them, the most precise you can buy in the world, to keep this thing as stable as possible. Because that minor shift that we talked about, this like part in a billion, is really a movement of the spectrum on your detector of only a few atoms in the detector of a shift. And that complicated onion layered thing we just can't really do here. But in terms of the optics and in terms of the mechanics and the development, this is a professional instrument, was built by a grad student here in our department. So he learned a lot and is actually on to the next bigger one, for that matter. And it's very nice to see locally students being able to do that kind of research in class or for their thesis, with an instrument that feels completely professional. It just doesn't have the temperature stability that the big one would have.
Very exciting stuff, Christian. Looking forward to seeing what NUID produces in the years to come, and even the Macquarie University Observatory as well. Thank you for beaming into Trekzone today. I really appreciate your time.
Thank you very, very much.
Welcome to Talkin Science. Dr. Matt Roth from the ANU is here to discuss the origin of gamma rays. Dr. Roth, thanks for your time.
Yeah, good morning, Matt. No worries at all.
This is Trekzone's Talkin Science. And you can get exclusive behind-the-scenes info and first-play access to all Trekzone podcasts by becoming a member today. Click join on every Trekzone video on YouTube. Go to thetrek.zone/support or scan the QR code on screen throughout the show. Now, it's back to you, Matt.
Well, thank you very much, Ross. And a quick mention of our socials: Trekzone's on YouTube, Twitter, Facebook, Instagram, and your favorite podcast feed. Find us, like, follow, and subscribe. Leave comments and ratings, and that'll help us convince the algorithm we're worth it. Matt, until now, it's been unclear what created gamma rays, which are one of the most energetic forms of light in the universe. You've busted the mystery.
Yeah, well, so this has been something we've been working on for the last year and a half. So essentially, what we've done is we've sort of modeled the emission from star-forming galaxies and worked out that it is, in fact, star-forming galaxies that produce this background emission.
So what does that modeling look like? Where do you start with a puzzle like this?
The basis for this whole project was essentially that we've sort of gained a better understanding of how cosmic rays, so these are just regular particles that move at relativistic velocity, so they have the velocities very close to the speed of light. And we've sort of gained a better understanding of how they move through the interstellar medium, which is the gas that sort of fills the galaxy between the stars. And it was sort of quite critical to understand, how many of them are actually converted to, how much of the energy is converted to gamma rays, and how many cosmic rays escape from a galaxy once they've been produced. So that was the fundamental bit.
Now, the origin of gamma rays have been stumping scientists for almost 60 years. Why was the answer so elusive?
Essentially, one of the problems that we've been having was that we used to sort of use a top-down approach to derive estimates for which classes of sources can produce the gamma rays and contribute to this gamma ray background that we observe. So what we tended to do was we looked at nearby galaxies. So there's about 15 star-forming galaxies that we can detect in gamma rays. And we take those and we extract from those what sort of how they would behave, how the emission would behave if we were to look out further into the universe. So that's what we call a luminosity function. So the same exact thing you can do for other sources. So for example, the biggest contender for this emission was actually active galactic nuclei, blazes in particular. So these are just the supermassive black holes that we see at the center of all galaxies. And when they accrete some gas, so when some gas falls onto them, they can produce these massive jets that shoot out the top and the bottom. And when one of these jets points towards us, then we get basically bombarded with these gamma rays from these AGN. And that was sort of the other big type of source that may be producing this gamma ray background. And you can do exactly the same thing. So you derive this luminosity function, and then you extrapolate from that out to sort of the earliest times when the first galaxies formed. And it turns out that the estimates were never really that tight. And then you can redo this, try try to improve here and there. Whereas our project was more of a bottom-up approach. So we actually model the emission for each galaxy, and then we apply that to a galaxy survey, and then basically look from the bottom up what sort of gamma ray emission we would expect to see.
Now, in its simplest form, what is a gamma ray?
So gamma ray is just a high-energy photon. So if to give you an example of how energetic. So if you take an infrared photon, so infrared we're all familiar with, it's just beyond the red, we can't see it, or we can feel it. So that has roughly an energy of 1 eV, 1 electron volt. Okay, so this is just an energy unit. So a gamma ray has an energy of 1 GeV, 1 giga electron volt. So that's 10 to the 9 times more energy. So this is just these are sort of the very highest energy photons we can observe. We can't actually observe anything much higher than that because there's a cutoff in the spectrum, simply because there are processes where sort of gamma rays interact with the photons from the cosmic microwave background and produce sort of lower energy radiation. So essentially, this is sort of the highest energy radiation we can observe in light.
And I guess probably something that we don't really want to be encountering in our travels around the universe, or really at all. If infrared can do that, and this is on a giga scale.
Yes. So gamma rays, X-rays, anything like that doesn't really mix with biology. So if we didn't have the atmosphere, we'd be in real trouble. And it is actually something that we need to consider for space travel, space flight. That the doses that astronauts receive from this radiation are contained within a certain range. Gamma rays are not sort of the biggest issue because that's relatively constant. That's relatively well easily forecast. Cosmic rays are more of an issue.
Well, I love when stories like these come up because we learn that, dare I say, well-worn equipment can still yield new results. Case in point here, where you use data from Hubble as well as the Fermi Gamma Ray Space Telescope. How do you piece together new and old data, and where does one go to get it? Is there a library of this stuff or something similar?
Yes, there is actually. So Hubble data, most of it is freely available to anyone. You just have to go to the right websites. You can download the raw data. You can download process data. Likewise for Fermi. So there's nothing we use that is not freely available. So the way this feeds into our model is that because we only, like I mentioned, we only observe about 15 star-forming galaxies and gamma rays, we need to go to some other spectral band. So Hubble usually operates sort of in the optical high infrared, near infrared, and we took data from there where we can actually look out to almost to where the very first galaxies formed, because the universe is essentially transparent in that energy range. So we take these galaxies. So we took 22,000. So this is essentially the galaxies observed in a tiny postage stamp in the sky. And we took them, we got some data for them. So we fed in things like the star formation rate that you can work out, the stellar mass was important, and the physical size, so the radius, if you will, of that galaxy. And that feeds into our model, and that produces a prediction for the gamma ray emission. And then once we've got this gamma ray emission, we just add it all up, in essence, make some corrections, some smaller corrections here and there, and then we compared it to what was observed with Fermi Lat over many years. But this is also heavily reduced data, because that's quite intricate to derive the background radiation from what the raw data that the detector actually detects.
And having said that this information is freely available, obviously it takes a trained mind to interpret it, a skilled mind to understand it even. What's it like to grab that old data and discover something new in there?
Yeah, look, it's there's the old phrase of standing on the shoulders of giants. So all the work we do builds on what happened before. So you just have to go to the reference list in the paper, and there's usually tens, if not 100 papers cited of other people that have done similar work or have done work that leads towards your result. It just shows that there are just open questions, all over the place, whether that's in astrophysics, in other areas of physics, or chemistry, biology. There's just so much that is still unexplored, and the more we know, the more we sort of know where these sort of niche areas are, where we still have a lack of knowledge, and where there's lots to contribute.
Now, just finally, Matt, what's the significance of gamma rays, and why should we keep studying them?
So the significance is that it does give us a very good picture of what happens sort of in the most extreme situations in the universe. So our research, for example, which is something we're currently working on, also makes predictions for neutrino emission, which are sort of very not very easily observed particles. They're very elusive, and it sort of allows us to probe some of the most extreme events in the universe.
Very important research indeed. Well, Trekzone membership costs less than a cup of coffee a month. It's available via the join button below on YouTube. For our podcast listeners, jump onto the trek.zone/support. And supporting me grow this channel gets you first play access and behind the scenes goss. Do it today and have my eternal gratitude. Matt, I really appreciate a little bit of your time to talk about gamma rays. Thanks for beaming in for this edition of Talkin' Science.
Thanks for having me on. Okay, have a good one.
Welcome to Talkin' Science interviews. Today, we're diving into the world of finding life on other worlds. New research has indicated almost 1,000 atmospheric molecules. Dr. Laurie McKemish is here to explain more.
On Apple Podcasts, Spotify, Google Podcasts, and YouTube for over 550 episodes. This is Talkin' Science.
Dr. McKemish, thanks for a little bit of your time.
No worries. Thank you for inviting me.
Now, can you tell us what is phosphine?
So phosphine is a molecule that has a phosphorus atom linked with 3 hydrogen atoms. So it's one of the simplest phosphorus-containing molecules out there.
And that key building block was recently found when scientists were poring over the 1978 Pioneer mission data to Venus. Why was that announcement so controversial?
So I think they went back and found the data in 1978 the recent data was they found some spectral lines using microwave spectroscopy, looked in the atmosphere of Venus, and the reason it was so controversial is because phosphine just shouldn't exist in Venus's atmosphere without something weird going on. So it should be destroyed by the sulfuric acid, and we don't actually know how it's produced in the first place. So you might have heard the stories about maybe it's life.
Exactly right. We actually covered it with Dr. Brad on our Talkin Science podcast. About the possibilities of life, and then the controversies that have followed from that about whether it is or it isn't. As you're saying, it shouldn't exist in Venus.
Yeah. Exactly. And so subsequent to that original discovery, there's been people thinking it might have just been SO2, which is much less controversial, or maybe there was a problem with the signal processing that was going on with the telescope.
Well, the great thing... Sorry, I'll let you continue.
The original authors, they're still debating that one. I'll leave them to it.
Well, the great thing with these molecules is that we don't have to go out there to find them, these phosphine and other elements. We can analyse spectral data of exoplanets to make these discoveries. So no great big science missions, but studying data. It's a little bit more mundane, but just as exciting.
Well, I think the really important thing is that you can look at planets just so far away that it'd take lifetimes and lifetimes to get there, and we can understand them just today. I would say that we really do want a big telescope up in space, which is kind of expensive, but you know.
But it's a lot cheaper than sending a mission out there and a generational ship, as it were.
Very much cheaper than that.
Well, you brought together an interdisciplinary team to understand how phosphorus behaves. What did you discover?
Yep. So my question when I heard about the phosphine is if we want to know whether it's some chemistry we don't know, some geology, some photochemistry, or whether it's indeed biology, you really need to understand what produces the phosphine and where the phosphine goes, so the sources and the sinks of the molecule. So I got together everyone I knew that might have had an interest in this topic and said, what do you think? And identified that actually there's not that many phosphorus-bearing molecules in the atmosphere of importance, or we don't know a lot about it. So really we just have to look for everything. And we produced the first data for almost 1,000 molecules. Very approximate data, but the first infrared spectra for many of these molecules, or the best current infrared spectra.
Well, the discoveries in your research will help follow up studies after phosphine is discovered to hopefully prevent the early hype like what happened to Venus earlier this year, won't it?
Yeah, so it's really about saying, okay, one molecule isn't enough. We need lots of molecules to really understand what's going on and prevent, yes, the headlines that go, we've discovered little green men on Venus. We're like, well, not quite yet. Sorry.
We are almost possibly there. Looking at the exoplanets, it's very exciting research. Dr. McKemish, thanks for your time on this Talkin Science interview.
Thank you very much.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favourite podcast app 5 days a week. Just search for Trekzone and subscribe.
Last week saw the crew for Artemis 2 chosen. This week, as they gear up to celebrate 50 years of Deep Space Station 43's support of both human and robotic missions, we have to check in with the Tidbinbilla tracking station. Even before the robotic lunar rover, which is being developed in Perth, the stalwart team at Canberra's Deep Space Communication Complex will be coordinating communication between Mission Control and this first crewed lunar flight in 50 years.
This is Trekzone's Talkin Science.
Well, to find out how preparations are going, Glenn Nagel is beaming in. Glenn, welcome back to Trekzone, mate. Busy times ahead down there.
Oh, it certainly is. It's been just in the last couple of weeks with visits by the NASA leadership and dealing with all of the different things happening with the Jet Propulsion Labs and missions upcoming, but especially with now the announcement for the Artemis 2 crew. And we're getting really excited here, and it's really putting a good focus on the work that we've been doing for the last couple of, years on upgrades to the site.
Yeah, absolutely. Well, we're still about 18 months away from the potential launch of this second mission. But how in advance do you plan, prepare and coordinate with the Deep Space Communication Network as a whole?
So we started doing planning work for the upgrades we need to do to the antennas probably about 6 years ago now. You need a lot of lead time. We've been adding new technologies to the antennas, increased bandwidths, higher bandwidths that we'll be using for the Artemis mission, new encryption systems that we'll be putting in because we're going to be carrying human spaceflight data again, as we did in the Apollo days, and making sure that we can get on top of things ahead of the game. So, because there's a lot of delays with the first launch of Artemis 1. We probably pushed back that launch date by about 14 months before we got to the final launch last November. And that was good because it gave us, in some ways, the additional time to actually get those first upgrades done on one of our 34-metre antennas. And now we're in the process of doing all the others.
Well, we've talked before about the pivotal role Australia played for the Apollo program. You mentioned it there, but just like NASA, it's been 50 years since there's been such a critical requirement, not just for comms, but the data as well, this astronaut monitoring. And we've also spoken about that as well, about, it's critical to have the robot missions and keep in touch with them. But when you start throwing humans in the mix, it becomes all the more critical, important privacy for these encryption and also staying in touch as well. We need to keep an eye on what the humans are doing out there.
Yeah, it's not only keeping an eye on the astronauts, checking all the data coming back from their biomedical sensors and the voice communications between the astronauts and mission control in Houston, Texas, but there's also, with human beings going away from the moon, and I think it was one of the important lessons they learned from Apollo, was to be able to have that actual personal contact. And one thing they'll certainly be doing in Artemis is providing more opportunity for the astronauts to talk to their families, talk to their friends, have video chats, email, sending text perhaps. And that's going to be an important part too. And that's why the encryption's there. And I think that's very important for people to understand. It's not trying to hide anything. We're not encrypting data. The mission, as was done with Artemis 1, will just be all broadcast live. You'll be able to go online, look at the cameras from the spacecraft, views from the outside, views from the inside, and it'll only be those times when the astronauts need privacy. During meal times, sleep times, and, special times when they might be talking to families and things like that, the cameras will be off, but there'll be lots of live press conferences and things going on. So nothing's being hidden from the public, but we need to look after the privacy concerns for those astronauts. And that's why those special encryption upgrades were happening as well.
Now, I'm guessing there's simulations and plenty of training ahead of the team working in the control room. You've had Artemis 1 to kind of do that dry run. Now we're getting into Artemis 2, putting the crew in the mix as well, going to lunar orbit, not landing, not doing that critical phase just yet, because it still is working all those little bugs out that might be coming up. Plenty of simulations too in the next 18 months.
Yeah, so before Artemis 1 launched, we probably trained for about 12 months going through all the different simulations and scenarios. People sort of need to remember that, we see the astronauts out there, we see the Houston Mission Control, but the Deep Space Network, our station here in Canberra, and the other two stations around the planet in Spain and the United States, are the vital link. And so if we're not ready, we're like when they, you'll see in the movies and you'll see in documentaries where they go, no-go for launch. You have to remember the Deep Space Network is one of those go-no-goes. So if you hear the call for network, you hear somebody go or no-go, that's us, not us directly. We're talking as a network as a whole. But it'd be great to hear the Aussie voice on there, the go-no-go for launch. You'd hear people going, go, go, go. And we go, yeah, we're right, mate. Go. Imagine that. I think we seem to stay a little bit serious while we're doing it.
Yeah.
So, and so all that training happens, and they throw a lot of interesting simulations in all the things that could go wrong. And one thing I think we've gotten really great at over the last 60 years of, space flight is we're now more prepared for, unlike an Apollo 13 where something they'd never trained for, happened, that it wasn't imagined to happen. But now with all that experience and through other missions in the Space Shuttle and the International Space Station, and even just the robotic missions, I think we're far more prepared now for the unknowns. There's been a lot more effort, a lot more thinking goes into that, and the scenarios that we've run through, in our simulations, in our training, throw some really extraordinary things at us from a communications point of view. We don't have to deal with all the extra stuff the astronauts will have to deal with. A lot of great planning in there, and especially for these astronauts who are going to be, well, first off, staying in a high Earth orbit before they leave. Check out the spacecraft, make sure it's okay before they go. That's very different to the days of Apollo, where they just basically took off and hit the engines and off they went. And then, of course, to go out beyond the moon. They'll be traveling further than any human's ever been before. And so this is, the extra importance of the Deep Space Network. Make sure we can talk to those astronauts at even these greater distances than we did during Apollo.
Well, Glenn, ever since we met back in 2005, I think it was, for a Channel 31 pilot that unfortunately didn't go anywhere, we've talked about the Deep Space Communication Network, the triumvirate that it is, Tidbinbilla with Goldston in California and Madrid in Spain, getting together and having that full planet coverage for data communication. Now that we're getting back into crewed missions, the biomedical data, the spacecraft telemetry, astronaut communications, that visual link as well needs to be back in mission control in real time. It is really a lot more critical than just the robotic missions. I say just in inverted commas.
If you lose a robot, well, you've lost a machine, and a lot of scientists and engineers on the ground are going to be incredibly disappointed. But to have humans in your hands, literally, and that vital contact, and not only just the contact with the astronauts, but all the telemetry from the spacecraft, monitoring all of its systems coming through, and making sure that the tracking is okay. We're going to be doing, literally down to the millimeter tracking with this spacecraft, the ranging we can do these days. So all of that, practice that we've had, all the experience that we have, the people here who, have been here for 20, 30 years in some cases, and even more, brings together hundreds and hundreds of years of space flight, spacecraft communication experience. And that's really, really important. It's as I said, a lot of people don't tend to think about the Deep Space Network. We're kind of transparent in a lot of ways. You'd only hear about us if we messed up. And so the important thing to the network is don't mess up. That's really, really, really key thing. I'll let you on a little inside thing. If anybody does mess up on a console somewhere, they get a little yellow rubber duck sat on their console until they've, paid a small penance. So there is a, important thing to people. Never get the rubber duck. That's an interesting thing.
So we've got those key performance indicators for the team in the network, and those rubber duckies to be looking out for if I am lucky enough to get inside a control room at some stage. I'm going to be looking for those, going through the frames of our vision. But certainly really interesting. Looking forward to everything that is ahead. Glenn, I guess a personal question for you. What are you most looking forward to as we get back to the moon?
Oh, look, so many things. I'll go back to the announcement of the crew. Seeing the entire astronaut corps there was just fabulous, and all the excited faces, and so many such young people, they're going to do incredible things. But, loved hearing with Christina Cook being announced, and Jeremy Hansen from Canada, and Reed Wiseman as the commander of the mission. But the person who I was most excited for was Victor Glover. I've followed his career. He's an amazing astronaut. He's an incredible spokesperson. If people have not watched the actual crew announcement, go and watch it just for Victor Glover's speech. It really showed the passion and the excitement he has. And I must admit, while each person was being announced, then Victor Glover's announcement, I just sat there with the biggest smile on my face and just went, yes, this is great. To see him actually going. He formally, gone to the space station, his career, just incredible. But as a representative of, for humanity, all of them are an amazing group of people, seeing their camaraderie and everything else. And I think that's the important thing. This will be a crew that will take all of us along for the ride. We'll be there every step of the way through the Deep Space Network, but the public will be able to be part of it as well, listening to all the communications, following on the journey, looking at all the amazing images, getting their feedback. So it won't be just all of us sitting back and watching some, fuzzy images on black and white television. This is going to be full color, high definition, and a real human journey that we can all be a part of, from the Earth to the Moon and back again.
Absolutely. Well said, Glenn. Great to chat. Looking forward to the next year and a half. As we inch closer to Artemis 2, we're going to be staying in touch and keeping an eye on what us Aussies are contributing to it.
Thanks very much. It's been great talking to you.
Welcome to Talkin Science. Dr. Danny Price from Curtin University is here to discuss the recent finding of earthbound interference in a signal detected from Proxima Centauri. Danny, thanks for your time.
Thanks for having me.
This is Trekzone's Talkin Science.
Well, don't forget Trekzone membership available via the join button under each video on YouTube or via the trek.zone/support. Plus Trekzone's on Twitter, Facebook, Instagram, and your favourite podcast feed. Find us, like, follow, and subscribe. Danny, let's start at the beginning. What was first thought to have been detected by Muriang in 2019?
Well, we did some observations of Proxima Centauri, which is our nearest stellar neighbour at about 4.2 light years away. We're using the Parkes Muriang telescope, and we sat on that data for a while because there was other stuff we were doing. We were looking for solar flares and doing a big multi-wavelength campaign with lots of different telescopes. But we set a portion of that data aside, the SETI data aside, to look for technosignatures, which are any signal that doesn't appear to be natural in nature and coming from outer space. And in 2020, my summer student, Shane Smith, went through that data and found something interesting. And it wasn't until December 2020 when the news kind of broke and the cat got out of the bag that we had found something interesting.
Very, very cool. Well, sometimes I don't like it when things get double checked because it means the original idea or results could be wrong. As it was in this case, I suppose it's better to know the truth, which was what exactly? What happened?
Well, we always, there's a very high bar before you can say this is life beyond Earth, and we hold ourselves to that. So we didn't let ourselves get too excited. But someone in the team did get a little bit too excited, and it was released to the media that we'd found something in December when really we probably would have waited a bit longer and until we were really ready to say what we thought it was. But this year, we spent, since that came out, a good 9 months just going through and analysing the data exhaustively, and we were able to say that it was something a lot more boring. It was radio interference from here on Earth. Interesting radio interference, a kind we haven't seen before, but radio interference nonetheless.
Now, I guess this is why Muriang, or the Parkes Radio Telescope, lives in a sheep paddock, Tidbinbilla 2. As Glenn Nagel once said to me, sheep don't have mobile phones or electric grids, but we still pick something up. How did the corruption happen into the signal?
Well, these telescopes are very sensitive. So Parkes had its 60th birthday this year, and since then it's tens of thousands of times more sensitive than it was when it was originally built. When it was originally built, it was already very sensitive. There's a statistic that the amount of energy that has been collected in the radio regime with telescopes is less than the amount of energy that a snowdrop would impart on the floor when it hits it. So that's just saying how incredibly sensitive these things are. And the signal we picked up was incredibly narrow band, meaning all of the energy was focused into one frequency. And we know this big telescope has essentially a massive gain. And so it's an incredibly faint signal we found. Some kind of interference from somewhere within the closest 100 kilometers. And it's probably some kind of malfunctioning radio amplifier.
And I guess that's the other thing as well. 60 years ago, Parkes was literally in the middle of nowhere and was perfectly situated. Now, as a society, spreads out and gets even closer, and not only that, we're also using more of the radio spectrum here on Earth with different types of radio broadcasting equipment. These things are going to crop up, I guess. Now, BLC-1 was the name of the detection. And as you say, it was thought to have found a technosignature. That's evidence of alien technology. Again, as you say, something not naturally occurring. In terms of postulating, Danny, do you think that those types of signals are out there somewhere just waiting to be discovered?
As a scientist and as a SETI researcher, my job is to answer that question whether or not they're there. So I'm not going to give you a definitive answer. I hope they're there. I think that there's life beyond Earth for sure. The question is, whether or not we can detect it, and whether or not intelligent life or life that uses technology or produces these kind of artificial signals is something we can find. That's a different question to whether or not it's out there. So, but fortunately, in our lifetimes, as long as NASA and the other space agencies keep going, we'll have an answer to whether or not there's simple life within the solar system. So we may find through different means that we're not alone.
Well, what's it like being part of the SETI search? Obviously, that is the whole mission, search for extraterrestrial intelligence. I remember as a kid that you could download the program onto your Windows 98 PC and run it as a screensaver, churning through the data. Now it's obviously getting bigger and bigger. It's, churning through a lot more information and a lot more recordings out there. But, another statistic as well is that we've only been searching for a couple of decades, and that really doesn't even get us to our nearest star of Proxima Centauri in terms of the speed of light.
As a scientist, it's kind of a dream job. When I was 12, I used to love this kind of thing, and I wrote a report on SETI, which I had completely forgotten about until my mum showed it to me a few years ago. I think it's a fantastic kind of science because it really engages the public into other astronomy and things, and it's something which a gateway essentially into other sciences. So we've had a lot of so the student who led the paper, for example, the BLC1 paper that we released was an undergraduate student, and hopefully he will continue and have a career in astronomy. And similarly, we collaborate with a lot of other astronomers because the kinds of equipment, the kinds of searches we need to do have very high resolution, and that high resolution is very useful for other science. And so it's really good in terms of technological development and development of skills as well as it just being an awesome science case. I mean, it'd be one of the most profound things. I'm really happy to be involved with the search. It's a lot of fun.
Yeah, absolutely. Well, the Breakthrough Listen project is the one that made this discovery, and obviously work continues on that, looking out and listening out for things in the future. Is there anything sort of coming up in the pipeline, any other sort of discoveries at the moment?
Yeah, so it's a 10-year project. We're about halfway through. The big thing coming up is we'll be turning the Meerkat telescope on, or our systems at the Meerkat telescope, which is a 64-dish array in South Africa in the Karoo Desert. And it's a fantastic new telescope that was built as a kind of pathfinder toward the ultra mega square kilometre array, half of which we're getting here in Western Australia. The other half will be going to South Africa. So we're turning on Meerkat, our systems there, and it will just be fantastically more sensitive. And we'll be able to do a new search where we can look at lots of different target stars at once. And the goal there is to survey 1 million nearby stars, so the local neighbourhood, and search for any signal that is in any way anomalous. Very, very cool. Well, Danny, I really appreciate your time on today's Talkin' Science. Good luck with the rest of the Breakthrough Listen project. Thank you. A carbonaceous chondrite meteorite was recovered in the UK recently. The recovery team in the UK were led by data from Australia's Curtin University. Dr. Luke Daly at the University of Glasgow joins me to chat about this very rare finding.
On Apple Podcasts, Spotify, Google Podcasts, and YouTube for over 550 episodes. This is Talkin' Science.
And Dr. Luke is with me now. Luke, thanks for a little bit of your time this morning.
No, thanks very much for having me. It's actually 9 p.m. where I am, so yeah, good evening.
The brilliance of the internet and video calls and time delays. We were chatting with someone last week, and I think it was very late PM for them as well. So from the bottom of the world, it is a welcome to Talkin' Science interviews.
Yeah, absolutely.
Now, tell us a little bit about this carbonaceous chondrite meteorite that was discovered. I understand that it's a pretty rare finding.
Yeah, so we had a carbonaceous chondrite fall on the 28th of February this year. It fell around 9:54, and it went basically splat into someone's driveway, made a little dent, and shattered into 1 million pieces.
Wow.
So yeah, it's a carbonaceous chondrite. It looks like it's a type of carbonaceous chondrite called a CM chondrite. And it's the first time anything like that has fallen on the UK ever. So it's possibly the most significant thing to happen to UK planetary science in history, which is awesome. And yeah, like you said, it was seen by a load of camera networks, including the sort of Desert Fireball Network expansion as part of the Global Fireball Observatory out at Curtin University, which sort of myself and Sarah McMullen at Imperial College London have been organising. So we saw this thing fall, along with all the other camera networks that work in the UK. Our friends over in Curtin University told us where it would be, and then we went out looking for it. And yeah, the result is this really precious space rock.
Now, there's a little bit of a connection for you with Curtin University, or another connection, if you will. You studied there, I believe.
Yeah, I did my PhD there between 2013 and 2017 with Professor Phil Bland and Professor Gretchen Benedicts. And that was looking at these self-same meteorites, carbonaceous chondrites, and all the minerals they kind of contain and what they can tell us about the solar system when these rocks formed 4.5 billion years ago. So yeah, very fond memories working with Curtin. I even helped set up some of the Desert Fireball Network cameras.
To have that come to fruition now with such accuracy, within 400 meters of the prediction of the Fireball Network, what's that feeling like to hit the ground running, as it were, and get within the ballpark to find this very important meteorite?
It's been unreal. I mean, like, we've been building the camera network in the UK for 5 years, and it's been about 3 years since we all started working together with all the other camera networks with this express aim to try and break the UK's duck of not having a recovered meteorite fall in 30 years. And there was a lot of doubt. A lot of people were saying, like, well, you can set the cameras up. We know the algorithms work because we've done it in Australia. Done it really well, recovered several meteorites in the outback. But are you really going to find it in a field or in a dark green deciduous forest or like in a boggy peatland of Scotland? Little black rocks, which is what meteorites tend to look like, don't stand out very well against a backdrop of sheep poo. Whereas in Australia, it's much better with the sort of like dark red dirt in the outback. That's got a really nice contrast for the eyes to see meteorites a mile away. Obviously, from experience searching in Australia, we have the problem with kangaroo poo and wombat droppings. They also have a similar affinity to meteorite fusion crust. But yeah, it was really great that we got this one. And not only we got the one that fell in a driveway, which you can kind of say, oh, yeah, that's easy, that's cheating. It slammed onto property, and it was pretty obvious when they looked out of the window in the morning that something was new in their world. We actually managed to get a team on the ground in a sort of COVID-safe way. Because of course, we're still in lockdown over here. We haven't got the leadership you've had over in Australia, unfortunately. And
it's a really sad state of affairs when Scott Morrison becomes the leader of the free world. But anyway, we won't go into that.
So it was great to get a team out to try and search this sort of really tight area that the Aussies had given us over at Curtin, saying it was about 4 square kilometers we had to search, and it looked like the thing fragmented on its way down. So as you saw that fireball blaze across the sky, it burst several times. So there should have been several more pieces, and unbelievably, really, we found a piece. I was actually part of the search team that found it on the day. It was my girlfriend next to me who found it herself. Like, she was like looking down, saw this unusual thing, and sort of like looked at me quizzically and was like, could this be it? And sort of like very quickly realized, oh my God, it is. You can see the fusion crust. It's this gorgeous specimen, and it's about the biggest bit we got, because instead of crash landing into concrete, it crash landed into soggy mud, so it cushioned the fall.
That really helps in terms of discoveries and samples that you can gather out of that. And one thing that I was reading in the press release was that the sample gathered here is very similar to the amount of sample returned, say, by the Hayabusa 2 mission, which landed back in December. And that one really fascinated me because in covering that story, I learned that there's only a few grams necessarily required to get an understanding of where these meteorites are from and what they contain. So how big was the sample recovered by your team?
So in total, what we've got is around 500 grams or half a kilo of material, which is 100 times more than they got from Hayabusa 2. So the data sets are going to be really nice and complementary. We got this carbonaceous chondrite in the UK within 12 hours of it falling. So no rainfall, no real effect by the weather. It's going to be pristine as you can get for a meteorite. And because the camera network saw it, like the Global Fireball Observatory, we're going to be able to figure out what asteroid it came from. So it's going to be really complementary to that Hayabusa 2 dataset. The good news is, like, as you say, absolutely, yeah, you can do a whole wealth of science with a very small amount of material if you put your mind to it. The great thing about having such a chunk now of this new carbonaceous chondrite is we can be a bit more sort of gung-ho with our analysis and do things like Hayabusa 2 would not let you do. To sort of really get into the guts of this rock and sort of start uncovering some of its secrets.
And tell us a little bit about carbonaceous chondrites for people that are unaware. They're obviously very special specimens of the early solar system, but what exactly can they tell us?
Yeah, so carbonaceous chondrites are a specific type of meteorite. They're one of the oldest rocks in our solar system, the oldest rock you'll ever hold. They formed basically within about 1 million to 2 million years after our sun first started to shine. So before they were kind of planets formed, there was just a swirling disk of gas and dust around the young sun. These were the first rocks that formed in our solar system. And carbonaceous chondrites, we think, formed in the outer solar system, kind of beyond Jupiter. And out there, water was in kind of its solid phase in ices. There's also a load of sort of organic molecules, amino acids, sort of fatty acids, simple sugars, graphite. Basically, these rocks contain all the building blocks and ingredients you would need to kick life off. So one of the kind of front-running theories is meteorites and or asteroids like this smashing into the early Earth as the early Earth was forming gave us the nice habitable world we see around us. So they gave us our oceans. They gave that primordial soup out of which life could sort of evolve and develop. So yeah, these are kind of really important samples for understanding both how asteroids develop, how we build planets, but also potentially how we build habitable worlds that life can get going and bring us all this wonderful diversity we see around us.
Well, there's some fascinating research to be had with this sample, half a kilo. That is absolutely awesome. And as you say, pristine in the fact that no Earth elements have really had a chance to sink in there and destroy the precious evidence that is lurking just beneath the surface. So, Luke, it's going to be fascinating to see the research come out on this one. We better let you go and get studying.
Yeah, no, there's plenty to do. We've got a huge consortium, like UK-wide, going into this rock. So yeah, hopefully we'll have some really cool results coming out very soon.
Welcome to Talkin Science, where we dive into science and space. We may have lost the Arecibo radio telescope in South America 12 months ago, but the data she collected is continuing to be studied. PhD student Jennifer Hardwick is here to discuss just one of those projects, an investigation into the fall relation. Jennifer, thanks for your time.
Thank you for having me.
This is Trekzone's Talkin Science.
Don't forget Trekzone membership available via the join button under each video on YouTube or via the trek.zone/support. Plus Trekzone's on Twitter, Facebook, Instagram and your favourite podcast feed. Find us, like, follow and subscribe. Jennifer, I can't believe it was a year ago that we lost the iconic Arecibo radio dish in South America, but her legacy lives on with data collected still being analysed by you and a team at the International Centre for Radio Astronomy Research.
Yep, exactly. I can't believe it's been a year. I remember when it fell down, it was quite traumatic, quite sad, but I'm really happy that we're still able to use this data and hopefully we'll still be able to use it for years to come. It's definitely a really great data set.
So this study is testing the relationship between the mass of stars in a galaxy and its rotation, with the current thinking that they directly correlate to each other. What can this tell us about how a galaxy will grow and evolve?
Yeah, so it's been proposed a while ago that this relationship between stellar mass and the rotation of a galaxy, or more scientifically we call it stellar-specific angular momentum, a bit of a mouthful, but the relationship between these two can tell us a lot about how galaxies form and evolve. It can tell us about how angular momentum, or the rotation, is transferred between dark matter and the galaxy. And what was really interesting about the study that we just published was that this relationship can also be affected by the types of galaxies that you choose to study as well. So previously, people thought that if this relationship changed slightly, then that would be it would be because of the change in the physics that we're assuming, but actually including different types of galaxies can also change this relationship, which is where our data is really cool.
Now, this full relation was first postulated almost 40 years ago, but previous research only had small samples and was limited by the galaxies studied. As you're sort of mentioning there as well, what you're studying can sometimes determine the data that results.
Yeah. For this sample, one size galaxy does not fit all. So we have to look at lots and lots of different types of galaxies in order to get the best picture of what's going on. So that's where other surveys were lacking in the past. They often would tend to focus on disk galaxies, which are kind of these nicely rotating galaxies, which are quite simple to model. But when we went and put in our sample lots of different types of galaxies, we had what we call elliptical galaxies, which are kind of a spherical shape, and they have a lot more random motions with the stars. When we include those types of galaxies as well, we find that this relationship wasn't what we first thought it was.
I guess one of the hardest things in this research is time. Needing to see the life cycle of a galaxy is a little difficult with our current linear progression of time as a human race.
Yeah, definitely. So in order to be able to kind of understand how a galaxy forms and evolve, we have to go and look at lots of different galaxies at lots of different stages in their life and kind of piece that together in order to be able to understand how kind of galaxies evolve overall. I mean, the life cycle of a galaxy can be billions of years, so it's not like something we can start recording and watch it unfold. We definitely need to, kind of be a bit more imaginative. And at the moment what we're doing is we're either taking observations of galaxies at different stages of their life and piecing it together, like I mentioned, or there are groups of people working on simulations, which is when you watch a galaxy evolve in a computer. But with this survey, we decided to mostly focus on observations.
And it's not as fun watching it in a computer simulation as to see it in real life data.
No, they tend to be a bit prettier in real life, I think.
Well, as I understand it, the data collected by Arecibo and sort of thinking in broad strokes here for astronomical research, all that data can be reanalyzed in the years to come as new techniques evolve for studying the universe. The next great step in collecting data will come with the Square Kilometre Array in WA and South Africa. But until then, this Arecibo data, I'm guessing, will keep you very busy.
Yeah, definitely. So we've got a pretty good data set here. We've still kind of got the most deep H1 observations, so the deepest observations of hydrogen from the Arecibo, and it'll definitely still be able to be used long into the future, just like the data we're using now that was collected back in 2017, I think, and we're still able to use it now, and it's still kind of cutting edge. So we're really hoping that we can keep using that data for a long time to come, even though the telescope, unfortunately, is no longer operational.
Exactly right. Well, Jennifer, good luck with the rest of the research. Looking forward to more things coming out as we learn more and more. Thanks for beaming in to this edition of Talkin' Science.
Thank you so much for having me. It was great.
Welcome to Talkin Science Interviews, the podcast where we dive into science and space. As the final instalment of 2021, it's time for Eclipse Show and a countdown of some of our guests from the year in absolutely no particular order.
This is Trekzone's Talkin Science.
And Professor David Flannery is beaming in for a Trekzone conversation right now. David, thanks so much for your time this morning.
G'day, thanks for having me.
Now, Hayabusa is coming. We're gearing up to this coverage on Sunday of the sample returning to Earth. It's going to be landing in Woomera. OSIRIS-REx is coming as well. That tagged asteroid Bennu a couple of months ago. And NASA has the Perseverance rover on the way to Mars for a sample return mission of its own. There's so many samples coming back to Earth from across the solar system. In your field of Earth sciences, what does that mean for you?
It's definitely a really exciting time to be alive. I guess it's worth remembering that we have had naturally occurring sample return missions from many of these bodies in the past, including the rocky planets of the inner solar system and asteroids, come to us in the form of meteorites. We're fairly sure we know where they're coming from, but to be able to go and get pristine samples ourselves really helps us peg our observations and test the hypotheses we've had for decades.
Now, can you tell us a little bit about the SAMI Galaxy Survey? It started 7 years ago. What was the genesis of the idea?
Yeah, so actually it started back in 2013. And I guess the genesis of the idea is that we really wanted to understand why galaxies look the way they do. It seems like a pretty simple question, but actually it's really hard to answer. And so we had a number of ideas about how what galaxies look like. For example, we've all seen images of galaxies from the Hubble Space Telescope and other telescopes like that. And they all seem to appear pretty diverse. So we see a number of different shapes of galaxies. They have a number of different colors. So they can be blue or red. When we see very blue galaxies, that means they're actively forming new stars, for example. Or if we see very red galaxies, that means they haven't formed stars generally for a few billion years or so. So there's a diversity of characteristics that galaxies have, and our survey was all about trying to disentangle what causes that diversity. So in order to do that, we needed to use about 250 nights on the telescope with an instrument called SAMI, the Sydney AAO Multi-Integral Field Spectrograph. We like our acronyms in astronomy, as you might be fully aware.
Yep.
So SAMI it allows us to take what's called integral field spectroscopy. Now, integral field spectroscopy is essentially we take an image of a galaxy, but for each point in the galaxy, we have a spectrum. So a spectrum, you might be aware, is where we break the components of the light up into its different wavelengths, much like a rainbow breaks up the light from the sun into its different colors, but much more granular. And so that allows us to make many different measurements of galaxies and try and disentangle the diversity of the galaxies.
Dr. McKemish, thanks for a little bit of your time.
No worries. Thank you for inviting me.
Now, can you tell us what is phosphine?
So phosphine is a molecule that has a phosphorus atom linked with 3 hydrogen atoms. So it's one of the simplest phosphorus-containing molecules out there.
And that key building block was recently found when scientists were poring over the 1978 Pioneer mission data to Venus. Why was that announcement so controversial?
So I think they went back and found the data in 1978. The recent data was they found some spectral lines using microwave spectroscopy, looked in the atmosphere of Venus, and the reason it was so controversial is because phosphine just shouldn't exist in Venus's atmosphere without something weird going on. So it should be destroyed by the sulfuric acid, and we don't actually know how it's produced in the first place. So you might have heard the stories about maybe it's life.
Bobby, you're the Deputy Director and General Manager for Science and Learning at Questacon, so you're in the best position to tell us about the centre and what it aims to achieve.
So Questacon, many generations of Australian school kids have been there. It's a typical journey that years 5 and 6 take from schools right across the country. They come to Canberra, they visit the national institutions, and the treat at the end of their big trip is often a visit to Questacon, which is a hands-on science centre with over 250 experiences and lots of really great and amazing experiences and staff here to help you. But beyond the National Science and Technology Centre in Canberra, we also have a National Technology Learning Centre, also here in Canberra, that reaches out across the country. And we take exhibitions, shows, workshops, dialogue and experiences out to schools and communities, large and small. Wherever you are, Questacon will be coming to you at some point.
Richard, we know that Tidbinbilla is a critical link for NASA's Deep Space Communication Network, providing one of 3 up and downlink facilities for spacecraft. But can you tell us about your specific role?
I'm part of the operations team in Canberra. I'm one of the operations team leaders. And essentially we have a crew of 16. And for daylight hours, currently that's 8 till 5, we'll control not only the Canberra assets, but also the assets in Madrid and Goldstone, the other 2 NASA DSN sites.
With so many missions currently out in the solar system and beyond, do you have a favourite spacecraft to talk to?
You have the nostalgic spacecraft and you have the exciting spacecraft. It's like going into a pub and picking out a particular person you want to talk to. If you look at the Voyagers, obviously we talk to Voyager 1, only Canberra can talk to Voyager 2 now, 22 billion kilometres away. That I've been in Canberra operations now for 32 years. And when I started, so Voyager 2 was just going through its Neptune encounter and now in interstellar space. So it's a spacecraft that I've spent my entire career tracking and hopefully probably until I retire. But then you have the other spacecraft like Parker Solar Probe, and which is a far more dynamic mission, I suppose. So getting so close to the sun and then sort of zooming out to almost the point of the orbit of Venus before flying back in again. So Voyager 2 will probably always be my favorite, but there's always something new, so the tracking of MSL so to Mars was incredible. So all the rovers around Mars are incredible, and we do those as well. And I should point out that it's not only the NASA spacecraft that we support, but it's also other agencies' spacecraft as well. We are tracking a lot of ESA spacecraft. CSIRO does manage the ESA site in New Norcia as well, and they have a single antenna. And we have a 70-meter and 3-beam waveguides, and we complement each other. So we are supporting a lot of ESA spacecraft because their network has almost hit saturation point, I think, especially with the Mars missions. But we also do the JAXAs, Arab Emirates is a new one, the Indian Space Agency as well. So, up till probably 6 months ago, we had mid-30 supports, but with Artemis being launched in November, hopefully, carrying 13 CubeSats, that's made life a little bit more interesting for us because now we're suddenly having these huge influx of the smaller spacecraft, which we still have to treat as the same as any flagship.
Well, Professor, what goes in must come out, but it turns out in the case of your research, we have clean elements becoming dirty ones. How does that work and what does it mean?
Well, the way it works is that, so it starts very early in the formation of the universe. The universe made a very clean system, mostly hydrogen and helium. And then over the course, stars started to form. And when a star forms, it turns that hydrogen and helium into heavier elements, carbon, nitrogen, oxygen, all the way up to iron, and everything that you're made of, everything that you see around you came from a star. And so that's what we astronomers call polluting the cosmos. And that happens in galaxies where you have this clean gas from the universe, initially from the Big Bang, accreting, falling onto galaxies. And then galaxies, they swirl it around and crunch it into stars. And then a few million years later, those stars explode and they shoot the gas back out of the top of the galaxy in polluting the cosmos even more. And so it's a constant cycle. And what it means is it means that galaxies refresh themselves, and over time they change the universe around them. They're not isolated, they're connected to the part of the universe that they live in.
Well, when we say exhaust, I think of what comes out of the tailpipe of a car. Is what we have here as toxic as that on a universal scale?
Not at all. It's quite the opposite. So everything that you see is that exhaust. So what comes out of the tailpipe of a car is quite bad for you. But part of the exhaust from a star exploding is the atoms that make you up, that made up the planets that we live on. And so even though it's polluting in terms of what an astronomer says, it's actually quite necessary and useful for promoting life and eventually creating new planets around new stars in other galaxies.
Now tell us a little bit about this carbonaceous chondrite meteorite that was discovered. I understand that it's a pretty rare finding.
Yeah, so we had a carbonaceous chondrite fall on the 28th of February this year. It fell around 9:54, and it went basically splat into someone's driveway, made a little dent, and shattered into a million pieces.
Wow.
So yeah, it's a carbonaceous chondrite. It looks like it's a type of carbonaceous chondrite called a CM chondrite. And it's the first time anything like that has fallen on the UK ever. So it's possibly the most significant thing to happen to UK planetary science in history, which is awesome. And yeah, like you said, it was seen by a load of camera networks, including the sort of Desert Fireball Network expansion as part of the Global Fireball Observatory out at Curtin University, which sort of myself and Sarah McMullen at Imperial College London have been organising. So we saw this thing fall along with all the other camera networks that work in the UK. Our friends over in Curtin University told us where it would be, and then we went out looking for it. And yeah, the result is this really precious space rock.
Ben, you and colleagues from the Netherlands have used their national observatory, Astron, to search for exoplanets, and it seems as though 19 red dwarfs are telling you a little more about themselves than expected.
Yes, no, we're super excited. So we used the world's most powerful radio telescope, LOFAR, to search the whole sky, or at least a large section of the sky, for radio waves from M-dwarf stars, that is red dwarf stars, the smallest kind of star. And quite unexpectedly, we found many radio bright, but circularly polarized, that is you pick them up with a circular antenna, radio sources. Now what's quite exciting is this is exactly what Jupiter looks like if you look at it with radio glasses on. So radio telescopes looking at Jupiter see circularly polarized radiation from its interaction with its moon Io. Io is whipping around in Jupiter's magnetic field, and it's driving this powerful aurora that you see with optical light, but you also see powerful radio waves. And so we think what we're seeing is a scaled up version of the Jupiter-Io interaction around these other stars.
My most humblest of thanks to each and every guest who beamed in across the year to discuss their research, the latest piece of news, or even just as a subject matter expert. It's been a real thrill to get to know so many people doing so much amazing work, and I cannot wait for 2022's season of Talkin Science interviews. This countdown is by no means, of course, all that we've done this year, so catch the Talkin Science interviews playlist to watch them all. And I'll see you for another edition real soon.
Welcome to Talkin Science Interviews. Matt Miller with you in Studio 4. Tomorrow, a Soyuz capsule designated MS-18 is launching from the Baikonur Cosmodrome. It's going to be carrying the next expedition to the International Space Station, including Colonel Mark Vande Hei. And he's beaming in for a quick chat on the other side of this.
on Apple Podcasts, Spotify, Google Podcasts, and YouTube for over 550 episodes. This is Talkin' Science.
Mark, thanks for a little bit of your time and welcome to Trekzone.
Oh, it's great to be here.
Thank you very much for a little bit of your time. I really appreciate it. You obviously have a job to do and you have a wealth of training to support you, but how do you prepare for launching into orbit and spending such a long duration on the space station?
Oh, I think you just have to pay attention to your mental health. I think for me, spending some time meditating every day, trying to figure out ways to help out other people is a great way for me to feel happy with myself. So just having a sense of service about every day and trying to feel like you have a way to contribute to the rest of the group that's useful will go a long way towards making it a very enjoyable time period for me.
Now, you're going to be flight engineer for this launch aboard Soyuz. What does that entail?
In the right seat as a flight engineer, my responsibilities are really just to back up the what I would call the commander and the co-pilot. I have access to the data about the spacecraft and training to understand what it means. So when I see something that looks at it like it's off nominal, out of sorts, I'll just raise to the attention of the commander and the co-pilot that, hey, this could use some more attention if I notice it before them. And then we'll work through the whole process together, but they'll definitely be the ones taking charge.
It sounds absolutely incredible. One thing I would love to do is jump aboard a Soyuz, any rocket, and head into space. Once you get there, a short trip to the International Space Station, relatively speaking, of course, and then you're going to be spending a few months on board the station. What are your objectives for this expedition?
My primary objective, like every other flight engineer on the space station, is to facilitate the science experiments that are happening on board every day. There's hundreds of them, and I like to refer to myself as a laboratory technician up there, facilitating the experiments on behalf of the scientists that can't be there with us.
Well, this is going to be your second trip to the station, having completed 4 months as part of Expedition 53 in 2017-18. Were there any lessons from those 4 months that you're going to apply this time around? Anything you learned on the station?
Yeah, I would say I learned a lot the first month I was in orbit about how to perform better. Lots of little things. Just managing things that can all float away from you is important. Even, I guess, kind of a funny story. I was the only rookie on the space station when I got up there. And the first time I opened up a bag of rice, all the rest of my crewmates started saying, wait, wait, wait. And I just tore open that bag of rice and the rice grains been flying all over the place. I now know that if I'm going to open something like that, I need to put some olive oil or garlic paste in there to serve as food glue so it all stays together and I can get it from my spoon into my mouth before it flies all over the place.
A little bit like Homer Simpson aboard the space shuttle in that episode of The Simpsons with the bag of chips. What about personally, Mark? Is there a moment, or do you have moments where you can just stop and look around you and see where you are floating high above the Earth, to look down on the Earth and know that everyone is down there? Do you have any of that sort of downtime to just contemplate everything?
Yes, definitely. Weekends are primarily off time. We have a lot of house cleaning to do on those, just like a lot of us do our errands on Saturday mornings maybe. But I love looking out the window. In fact, my first orbit around the planet after I got to the space station, we were supposed to go to sleep right away, but I could not get myself to go to bed right away. I was just so excited. And I spent the first 90 minutes on the space station staring out the window. It's just indescribably beautiful. It looks so close, but I could look at the entire peninsula of Italy in one glance when I was up there. So it's the scale is just hard to get your head wrapped around.
Well, with Crew Dragon about to enter mainstream service as NASA's way into space, do you think launches on the Soyuz will be missed?
I hope that we continue to operate on multiple spacecraft. It gives us redundancy, and as more commercial companies are successful with that, then I hope we trade those seats back and forth so that we can continue to cooperate, give the Russians more redundancy by using our spacecraft, and continue to have that skill set that I have right now to launch as a crew member on a Russian spacecraft.
Fantastic, Mark. Well, thanks for a little bit of your time. Good luck on the expedition. Really looking forward to seeing everything unfold for you.
Thanks very much. Great talking to you today.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favourite podcast app 5 days a week. Just search for Trekzone.
Widely considered to be the successor to the famed Hubble Space Telescope, the James Webb Space Telescope launched successfully yesterday to embark on a 1.5 million kilometre orbit around the Sun.
This is Trekzone's Talkin' Science.
Well, don't forget Trekzone membership available via the join button under each video on YouTube or via the trek.zone/support. Plus Trekzone's on Twitter, Facebook, Instagram, and your favourite podcast feed. Find us, like, follow, and subscribe. Well, development on the James Webb Space Telescope began in 1996 for a launch that was initially planned for 2007 at a budget of $500 million US. The project has endured numerous delays and cost overruns, including a major redesign in 2005, a ripped sun shield during a practice deployment, a recommendation from an independent review board, the COVID-19 pandemic, issues with the Ariane 5 rocket, and the telescope itself, as well as even a naming controversy where the telescope's namesake was alleged to have been complicit during the Lavender Scare persecution of LGBTQ employees in the US government departments during the Truman administration. Following a 6-month investigation this year, NASA declined renaming, with former administrator and person responsible for naming, Sean O'Keefe, denouncing discrimination against talented professionals on the basis of their personal preferences, additionally noting that to suggest Webb should be held accountable for that activity when there's no evidence to even hint is an injustice. One member of NASA's Astrophysics Advisory Committee resigned in response to O'Keefe's comments. However, despite all of that, as well as forecast storms this week, on Christmas morning, the telescope launched atop a European Ariane 5 rocket from French Guiana, bringing astronomers closer to distant galaxies than ever before. And unlike the Hubble telescope, which observes in the near ultraviolet, visible and near infrared spectra, the James Webb Space Telescope will observe in a lower frequency range from long wavelength visible light through mid-infrared, which will allow it to observe high redshift objects that are too old and too distant for Hubble to observe. It'll take a month to get to the Lagrange point, or L2, and another 5 months before its infrared eyes are ready to start scanning the cosmos, and so far, all telemetry is nominal. Telemetry, in fact, relayed from the Space Telescope by NASA's Deep Space Communication Network.
Yeah, so going out to the L2 Lagrange point, around about 1.3 million kilometres away, so well beyond the orbit of the Moon, the Deep Space Network is the only system in the world capable of talking to spacecraft at these great distances.
Our friends at the Tidbinbilla Tracking Station, one of 3 in the Deep Space Network, received the first telemetry from James Webb.
With the spacecraft launching from French Guiana, it comes over from the west to east, so Canberra is the first station in line to be able to provide two-way communication with the spacecraft.
The University of Queensland's Dr. Benjamin Pope said such a powerful space telescope will put us on the doorstep of some incredible discoveries, and he'll be just one of the many astronomers lining up to use the data collected by the telescope. At such a distance, the signal-to-noise ratio becomes incredibly critical, but it's not noise in the signal from the source, but rather at the receiving end.
The biggest problem is actually other types of noise. Literally here on Earth, radios, televisions, mobile phones, and so on. So we do a lot of processing to eliminate that data. So as long as we're tuned in to the spacecraft in its correct frequency and it's sending back its data correctly, we will be able to receive it here at the DSN and our stations around the world in Spain and California, error-free.
With 11 rovers on Mars and various other missions around our solar system, it's a busy time for the Deep Space Network.
And we've got about 4 or 5 currently at the Moon. With James Webb's going to the L2 Lagrange point, it's heading there with other spacecraft in that sort of region, the missions that are studying the Sun
and other craft from different nations.
The James Webb Space Telescope has been a mission over 10 years in the planning, at least this version. And with rapidly changing technology and even operational procedures evolving, training for this mission started 2.5 years ago.
But we have to train, just like an astronaut would train for a mission, we train for all the different communication scenarios that can happen with a spacecraft, all of its different fault and safe modes, because we're really the first point of contact so that we can start to analyze what is wrong with the spacecraft, know who on the mission to be able to actually then contact to then look after their craft if the problems are more serious. So think of us as being air traffic control for space, and you're very handy celestial troubleshooter.
The hardware for James Webb was locked off years ago, but the software was in a constant development cycle, with Australian scientists contributing to improve key components.
So NASA, of course, would use their own proprietary software. We generally wouldn't use Windows on a spacecraft. The help desk takes too long to get through to. But the spacecraft would have had its technology locked down quite a few years ago. And while the hardware wouldn't have changed, you can do a lot of upgrades with software. In fact, Australian scientists at some of our universities, the University of Sydney and Melbourne, have actually created some interesting software for the spacecraft to actually improve the optics, so that the mirrors, and you know that James Webb has those 18 separate mirrors acting as one. Australian technology is going to allow those mirrors to actually act independently as well, increasing the volume of science data that can be returned.
The James Webb Space Telescope goes boldly to an orbit in our solar system where a handful of other observatories lay, quietly studying our universe to give us an understanding of what's out there, and that, through it all, is worth every cent spent in the budget and every drop of sweat from engineers, researchers, programmers and communications specialists. We'll bring you more Webb news as it happens here on Talkin Science, Trekzone's home of science and space news. Welcome to Talkin Science, where we dive into the latest news from space and science. Tidbinbilla's Richard Stevenson has beamed in. I'm very excited for this chat. Richard, thanks for your time.
Thank you, Matt.
Well, before we get into it, a quick reminder that you can get behind the scenes goss and early access to all Trekzone podcasts by becoming a member today. Click the join button on any Trekzone video, go to the Trekzone/support, or put your phone up to the QR code on screen throughout the show. Richard, we know that Tidbinbilla is a critical link for NASA's Deep Space Communication Network, providing one of 3 up and downlink facilities for spacecraft. But can you tell us about your specific role?
I'm part of the operations team in Canberra. I'm one of the operations team leaders. And essentially we have a crew of 16. And for daylight hours, currently that's 8 till 5, we'll control not only the Canberra assets, but also the assets in Madrid and Goldstone, the other 2 NASA DSN sites.
With so many missions currently out in the solar system and beyond, do you have a favourite spacecraft to talk to?
I mean, yeah, you have the nostalgic spacecraft and you have the exciting spacecraft. It's like going into a pub and picking out a particular person you want to talk to. If you look at the Voyagers, obviously we talk to Voyager 1. Only Canberra can talk to Voyager 2 now, 22 billion kilometres away. That I've been in Canberra operations now for 32 years. And when I started, so Voyager 2 was just going through its Neptune encounter and now in interstellar space. So it's a spacecraft that's I've spent my entire career tracking and hopefully probably until I retire. But then you have the other spacecraft like Parker Solar Probe, and which is a far more dynamic mission, I suppose. So getting so close to the sun and then sort of zooming out to almost the point of the orbit of Venus before flying back in again. So Voyager 2 will probably always be my favorite, but there's always something new, so the tracking of MSL so to Mars was incredible. So all the rovers around Mars are incredible, and we do those as well. And I should point out that it's not only the NASA spacecraft that we support, but it's also other agency spacecraft as well. We are tracking a lot of ESA spacecraft. CSIRO does manage the ESA site in New Norcia as well, and they have a single antenna. And we have a 70-meter and 3-beam waveguides, and we complement each other. So we are supporting a lot of ESA spacecraft because their network has almost hit saturation point, I think, especially with the Mars missions. But we also do the JAXAs, Arab Emirates is a new one, the Indian Space Agency as well. So, up till probably 6 months ago, we had mid-30s supports, but with Artemis being launched in November, hopefully, carrying 13 CubeSats, that's made life a little bit more interesting for us because now we're suddenly having these huge influx of the smaller spacecraft, which we still have to treat as the same as any flagship.
Well, how does the relay back to each missions control work? Is it real-time with each DSN station as a conduit, or is it more like a buffer where you receive the set of instructions and pass it on?
It differs from mission to mission. It depends. Some missions might need that real-time feedback. We have the Chandra, telescope, which is obviously a real-time support. They'll send commands. They need to see those acknowledged in their telemetry to send other commands. So that's a real-time support. But we also have supports like Geotel, for instance, where it's a regular support that comes up, and we'll track it, we'll record the data, and then when project comes in the following morning, they can grab it on their PC. The whole network works like a spoken hub, so all the data coming down from Canberra, Madrid, or Goldstone goes through the JPL hub. So if you are a project, you would actually subscribe to data from JPL, and they deliver it to you.
What about weather? How does that play a part in communications? You're obviously receiving and transmitting on long wavelengths, so I'm guessing the light weather, not so much, but what about when it gets really heavy down there in Canberra?
Well, we actually sort of track on 3 discrete bands for spacecraft. Sierra band is 2.2 sort of gig, and it's big and robust. It's, I should say, fairly long wavelength in relatively. So we're not really concerned about weather there. X-ray band, we have to be careful with the rain. Light rain is okay. Heavy rain can wipe out a signal. And then it all comes down to margins. If a spacecraft has a big booming signal, obviously it can ride the rain or surf the rain. But if you're looking at spacecraft that are right on the hairy edge, for instance, the Voyagers, then that can be the difference between receiving good data or a total washout. We also have, and that's the 8 gig, when you go up into the 26 or 32, which is our K-bands, that can be, we can actually see degradation with heavy cloud going over. And certainly, so anything more than a very small sprinkle of rain can wash it out completely.
Now, we've had a few missions land on Mars this year, plus Hayabusa 2 returning from asteroid Bennu in December. OSIRIS-REx leaving its asteroid home 2 a few weeks ago. Is it more exciting to hear from the spacecraft or rover at those milestone points, or getting the reaction from the humans waiting anxiously for the news?
For us, it depends on, I said, the milestones of the mission. So with Hayabusa, it was one after the other. I mean, so they really did sort of nail that poor little asteroid with everything from little tags flying down to ballistics to finally scooping up and returning. With OSIRIS-REx, so it wasn't quite so ambitious, but they've got their sample now and returning as well. So you've got these projects with lots of little milestones. And obviously, if you look at New Horizons and the Pluto mission, that milestone took 9 years. So you're not holding your breath for that. With the Mars missions, obviously the landings are the most exciting, but then you have the little key milestones with, for instance, the new helicopter as well, which was incredible. All of which comes through our relay spacecraft around Mars. We do have Mars Odyssey and Mars Reconnaissance Orbiter that act as a primary relays. But we can also use the ESA spacecraft as well, MEX and TGO, Trace Gas Orbiter, to also relay that UHF signal to Earth through the Electra system that we have around Mars.
NASA's Artemis program is gearing up for lunar missions in the next few years. I'm assuming Tidbinbilla will once again be providing critical support. Like the Apollo missions, what's the buzz like around the place?
There is a buzz, but we're not sure why. We haven't really had a huge amount of clarification. The DSN SCAN, which is essentially the NASA agency that's responsible for all spacecraft communications, has three networks. They have the near Earth. They have the TDRS network, which covers spacecraft fairly close to Earth, and then our Deep Space network. When you're looking at what's required for Artemis and Luna, so it's a cross between close Earth and deep space. The optimal antenna size is around about 18 meters, and we have 34 meters. So the DSN may support a little bit differently to our normal spacecraft. But yeah, look, it's going to be an exciting mission. We will be supporting it. We were told that a few years ago. We are now human spaceflight certified, so we can pass data from human spaceflight back to JPL as well. So we're just hoping that obviously the November launch won't be crewed, but hopefully the next ones will. And when I first started in Canberra operations, so 30 odd years ago, we were still doing shuttle. And before the TDRS network kicked in, and so meant that they were talking directly to White Sands, we did actually communicate with astronauts, and it'd be interesting to see so whether I get to speak to another astronaut before I retire.
Obviously, there is a difference between talking to robotic missions and talking to humans. Having that feedback as well from astronauts. So you say you work with the shuttle. What's that like to have that two-way communication with a mission?
Brief. with the shuttle, it was very brief. Essentially, with it being such low Earth orbit, so they are more or less from horizon to horizon within 5 or 6 minutes. So you had just enough time to say good day and thank you very much before they disappeared over the horizon. And they actually used to disappear over the Pacific, and they were entering their zone of exclusion at that point, which is why the TDRS network came out and took that away. So it was like an umbrella system sitting above shuttle, and each one relayed down to White Sands. So they had continuous coverage as they orbited. But no, it'll be different. And I said, so we know we're doing Artemis, but we're not sure whether it's a 24/7 coverage, in which case we have to start allocating assets. We're not sure whether, obviously from Artemis 1 or EM1 to the time there is a crew on the next one, there may be an opportunity to build a smaller antenna at each site that could possibly be committed to the lunar missions 24/7.
Richard, very exciting times ahead indeed. Looking forward to hearing more about our role and our supporting role of these missions. As you say, not just NASA, but ESA missions as well, and other space agencies coming online as well. So many missions happening in the solar system. Thanks for a little bit of your time this morning as part of Talkin Science Fest, and hope we can chat again real soon.
Pleasure. Catch you later, Matt.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favourite podcast app 5 days a week. Just search for Trekzone and subscribe.
Well, welcome to the first Trekzone TV live stream event for 2023. Matt Miller with you, and I hope you've been enjoying this spectacular shot of the sun as the moon slowly made its way between us. I begin today's broadcast by acknowledging the traditional custodians of the Ningaloo land on which this awesome astronomical event unfolded with our cameras, all thanks to time and date, the Perth Observatory and the Learmonth Solar Observatory. I also pay my respects to elders past and present. A huge thanks to timeanddate.com, as I said, the Perth Observatory and the Learmonth Solar Observatory for giving us access to the clean feed of the eclipse. It allows us to bring you this pretty rare hybrid event. Now, the partial eclipse began at 11:34 Brisbane time, with the full eclipse underway from 1:37. Maximum eclipse or totality is at 2:16. That is in a little over half an hour from now, and everything will wrap up at 2:56, with partial eclipse ending just before we go off air at 4:59 this afternoon. I think it's a little bit later now, but we're going to be off air at 5 p.m. this afternoon. This live component is just my chat with Dr. Stuart Ryder and talking to you about the solar eclipse, and then we'll take you straight back to the archive of Talkin Science interviews, keeping this live shot going as well. Now, the path of totality passes over Northwest Cape, a remote peninsula of Western Australia, and the only place to see the eclipse in its full natural beauty is Exmouth on the Ningaloo Reef. The process of the moon moving across the face of the sun takes 3 hours, but the brief moment when the sun is completely obscured by the moon lasted only 62 seconds. That is the path of totality. There are 4 types of solar eclipse: total, annular, partial and hybrid. The hybrid solar eclipse is the rarest and occurs when the distance between the Earth and Moon is so delicately balanced that the curvature of the Earth comes into play. Now is a great opportunity to mention our new podcast offering just before we get to Stuart Ryder. That podcast offering is live now. Find each of Trekzone's shows on Google or Apple Podcasts, Spreaker, iHeartRadio and more. You can also find our channel on the iTunes library for a one-stop shop of all of Trekzone's goodness. Memberships are available both for early access and behind the scenes of our new Star Trek fan film, and our social media feeds have podcast highlights and Star Trek episodes. Get all the details over on Trekzone right now. Plenty of exciting stuff still to come this year, including a new season of watch parties, and of course, I've been harping on about it on Trekzone TV for a long time. The 20th anniversary of Trekzone celebration, Monday, July 10. All right, let's get on with the show here now. Talkin Science, we're here for the solar eclipse. The main star is that eclipse happening that way. And it's not going anywhere. Might flicker there every now and then, but Time and Date are really looking after me. I really appreciate that. It is time for today's guest. Adjunct Fellow in the School of Mathematical and Physical Sciences at Macquarie University, Dr. Stuart Ryder beamed in last week to chat about today's event. I began even by asking him why the hybrid event is so special.
Good morning, Matt. Well, it's unusual because it's kind of a mixture of the 2 types of solar eclipses that happen here on Earth, and it all depends on the relative distance between the moon and the Earth and the sun. So the amazing thing really is that the sun is 400 times further away in the sky than the moon is, but it's also 400 times larger. So as you probably mentioned, the fact that we get eclipses, total eclipses at all, is something of a remarkable coincidence. But sometimes, because the moon's orbit is not a perfect circle, it's a little bit closer to us, and so it may not completely cover the sun if it's a bit further away in its orbit, for instance. And in this particular case, depending on where you are on the surface of the Earth, at the beginning and end of the eclipse tracks, the moon won't quite be large enough to block the sun out completely, and anyone at those locations, of course, well, they're actually out in the middle of the oceans, but anybody there would only see an annular eclipse. The sun would appear like a ring of fire, just a very thin piece of the solar surface still visible. But for those lucky enough to be near the centre of the eclipse path, in particular those in Exmouth region on April 20th, just the curvature of the Earth is enough to bring those people a little bit closer to the moon, and that makes the moon big enough to completely cover the sun, although only for about a minute. And at that point, they'll be able to see this wonderful corona, the outer atmosphere of the sun, that you simply don't get to see during an annular or a partial solar eclipse.
And I think the really interesting thing with Earth covered by so much water, it is very rare as well for people on land to get an absolute total solar eclipse. What I find fascinating is that it's just 1 minute, and there are so many people from around the world travelling to Exmouth to experience this. Have you yourself seen a total solar eclipse?
Yes, I've been fortunate to travel to different parts of the world over the last 30 years or so, and I've been to 12 solar eclipses. Unfortunately, the weather doesn't always cooperate, and I've only been able to witness 10 of those eclipses, although that's still a pretty significant number of eclipses. It's something just over half an hour that I've managed to spend in the moon's shadow, which is it's a pretty spectacular sight, and something you never quite seem to get enough of. But unfortunately, I won't be one of the tens of thousands piling into Exmouth for the eclipse next week.
Certainly a very, very interesting experience, Western Australia, Northern Territory this time around. Not very often it happens for us here in Australia, so that's great. But we should, of course, have our public safety warning as well for those around that are going to be witnessing the annular eclipse. Staring at the sun is never advisable at the best of times. What's the best way to view the eclipse?
Yeah, right. So pretty much from anyone elsewhere in Australia, apart from that narrow tip of the Exmouth Peninsula, is not going to see that wonderful totality. It's never safe to look directly at the sun. But pretty much everywhere else in the continental part of Australia will get to see what's called a partial eclipse of the sun. So the percentage of the sun will be covered, down to about 10%, 20% in Sydney, Melbourne sort of area. And I think only Tasmania will miss out completely. But it's simply too dangerous to try to view that in any direct way. Probably the safest option would be, I'm sure, a lot of astronomy societies, amateurs who love showing the sky to people. They will have safe solar system viewing setups. So go online, find out what the plans are at your local astronomy society or local observatory, and they will have a setup that is either what we call a projection, so that the image of the sun through the telescope is projected onto a screen that people look at the sun. They don't look directly through the telescope. There are some telescopes that are manufactured that have a special filter built into them, or that can be attached by a qualified person that does make it safe to view the sun directly. But really, the risk of damaging your eyes just for that opportunity to see a chunk taken out of the sun, it's really not worth it. But as I say, there are definitely safe options. And the other one, of course, is to go online and look for a live stream of the event. There's bound to be several of those, including some from the Eclipse Totality zone in Exmouth. But trust me, seeing it on a computer screen isn't the same as experiencing the eclipse, because it's not just about the light visual effects that you get. It's the fact that you feel the temperature goes down in the middle of the daytime, which is really eerie. It's the fact that birds and animals think that evening has come, and so they start to go about their roosting behaviour, and then seconds later they have to wake up again. So and even just the reaction of the people around you, people who are normally quite sane and rational, but they get very emotional when they witness a total solar eclipse, trust me.
Doc, I've got to ask as well, so the last time this hybrid event occurred was in 2013. Next time won't be till 2031. Plenty of time to prepare for the next one. Do we know where we need to be in 2031?
Yeah, well, in fact, hybrid eclipses, well, they're somewhat unusual in their characteristics, but the majority are actually what are called the total solar eclipses, and they can last anywhere up to 7.5 minutes. Indeed, we're very fortunate. Let me just bring out my special eclipse globe. So this globe for the Earth is a bit unusual in it. It has the paths of all the solar eclipses for the next couple of hundred years marked on it. And in fact, from here in Sydney, for instance, we'll be very fortunate that there'll be a total solar eclipse passes directly over us on the 22nd of July, 2028. So lasting almost 3 minutes. So that potential there for many millions of people to witness the eclipse, even if they just stay at home, should be pretty high. But it does, before that, of course, it crosses a large part of central Australia as well, and arguably the weather prospects for fine weather, which is really what you need, are somewhat higher there. There's another one in 2037, there's another one in 2030, which cuts through South Australia and then up to Queensland. And then there's another one in 2038 that, again, crosses through southern Victoria. And a number of these also then the paths cross over New Zealand as well. So it's a bit of a golden age for eclipses here in Australasia. So if you're not successful this time around, or you don't have the chance to see the one on April 20th this year, then don't worry, there's several more coming to Australia and New Zealand in the next few years.
Well, Dr. Stuart Ryder there chatting with me for Talkin' Science last week. He's an adjunct fellow in the School of Mathematical and Physical Sciences at Macquarie University in Sydney. Expert reactions on this eclipse were documented by the Australian Science Media Exchange yesterday, and a handful of them include Professor Michael Wheatland saying that for most of Australia the eclipse will be partial. In Sydney there will be, and there has been at most, about a 19% coverage starting at 1:37, so about 20 minutes ago. Which is very, very cool. Dr. Kat Ross at the International Centre for Radio Astronomy Research added that this is a wonderful example of the incredible role WA has in observing the local astronomical neighbourhood and exploring the depths of our universe. Professor Melanie Johnston-Hollett at the Curtin Institute for Computation is eagerly awaiting today, or she has been eagerly awaiting today. I hope she's had a fantastic day, noting that this is a tangible experience that demonstrates the structure of the solar system and that we are on a rock being orbited by another rock, both of which are orbiting a star in the vastness of space. Now, while we wait for the cosmic ballet to complete its dance across the sky, as Mr. Nimoy said in a Simpsons episode, it's a great opportunity to mention our new podcast offering, which is now live. I just want to drive this point home because I've had to change stuff up. It's no longer one Trekzone feed to the podcast networks. It's now show specific. So you need to jump onto your podcast feed of choice and resubscribe to Trekzone. That's going to limit the notifications. If you only want our fan film updates, well, you don't need to get Talkin' Science updates, do you? So that's the advantage of that. It's also a much better way of doing stuff, and a huge thanks to iHeartRadio for having us on board their platform, their global platform, which is fantastic. So Google or Apple Podcasts, Spreaker, iHeartRadio and more. Wherever you get your podcasts, we are there. If we are not there, send an email to editor@trekzone.org and I can definitely work on that for you. You can also find our channel on the iTunes library now as well. That's a one-stop shop for all of Trekzone's goodness. Something I didn't realise was available. It's now there, which is great. Memberships are also available on YouTube, both for early access and behind the scenes of our next Star Trek fan film. And our social media feeds have podcast highlights and Star Trek episodes. Get all the details over on Trekzone right now. Basically find us, Trekzone Media, wherever you're social, we're there as well. Plenty of exciting stuff still to come, including a new season of watch parties here on Trekzone TV. Samuel Cockings is going to be beaming in. Trek Shorts watch parties are coming up. Be on the lookout for those. Of course, 20 years of Trekzone in July. It is 3.5 months away, but I'm going to keep banging that drum because I want it known out there in the public that that is happening. We've been around for 20 years. 2003, I started. I remember the morning. I grabbed Dad's credit card and I signed up at GoDaddy for Trekzone.org. That was July 10, 2003. I was in year 10 and was part of an IT project. So there you go. Well, Starship is planning on launching tonight my time as well. That's going to be exciting to see the largest rocket humanity has built. Hopefully lift off this time. Hopefully they've worked on that stuck valve. Plus Picard's finale tonight. Strange New Worlds Season 2 trailer dropped this morning as well. Section 31 movie with Michelle Yeoh. That's coming up. There's so much to discuss on the next podcast. So I've got to get in touch with Dr. Trek and get him back in to chat about all this awesome Star Trek news that is coming up. And apparently there is going to be something tonight as well. So the rumour mill goes. They're going to announce something hot off the heels of the Picard finale. So we're going to be keeping you on across all of that with Dr. Trek in the next couple of weeks. For now, though, that is where I'm going to leave you in the capable hands of our trusty Trekzone TV automation. Thanks for watching this live edition of Talkin' Science, or indeed in the future as well if you're watching. I'm Matt Miller. I'll see you for more real soon. Stick around because we're going to be staying with the eclipse for another few hours yet as that moon completely makes its way out of the sun's way and we can get back to enjoying the fruits of the sun's labour. We're live. I don't know what I'm trying to say. I'm just looking out the window here at Trekzone's studio. It's a bit cloudy, so no eclipse for us here in Brisbane, but thankfully I've got the Trekzone TV live stream, so I've been able to enjoy the podcast, been able to enjoy the stream and watching this awesome eclipse. A huge thanks once again to timeanddate.com, the Perth Observatory and the Learmonth Solar Observatory. Absolutely incredible to watch that 60 seconds of totality. Incredible that that's all it is, proving that this isn't a flat earth. 100% by the way that this all works. Time and Date going through their motions there with other locations. They've got a couple of cameras up, it seems, which is great. So once again, I really appreciate the team that have done that for us. I'm holding back a sneeze until we get off air. So this is where we're going to wrap it up. Stay with Trekzone TV because we are streaming 24/7. It's a fast channel, free ad-supported television. There's no ads just yet. I don't want to say ad-free forever. That's the website. Hopefully there'll be some ads on this stream in the very near future. I know you're not going to be thrilled with that, but that means that I'm getting some money for this hobby, so that's something that I really want to see. But yes, that is Trekzone TV, fast, free ad-supported television. A lot of the networks are doing these now, over-the-top transmissions, dedicated stuff as well. We've been going through the Trekzone archive. There is so much content to enjoy here on Trekzone. Over 1,050 episodes. By the time we get to the 20th anniversary, it's going to be well over 1,100 episodes of content, chatting with all sorts of people, Star Trek alum. We've had science people, we've made discoveries, we've learnt a lot of stuff, we've played some Star Trek games, done so many great things on Trekzone. I'm so looking forward to celebrating it all on July 10. And of course, those watch parties coming up, the short Treks, the Trek Shorts watch parties with Samuel Cockings, hoping to dive into those in the next couple of weeks. Stay on Trekzone TV for the absolute latest. The thumbnail is going to change with those times as we get closer. We're also going to be doing it, streaming it as well on our Facebook page. So follow us there to get the absolute latest and get a glimpse and get reminders as well of when we are going to be doing these streams, because certainly coming up. Want to do a lot more, want to get people involved in this and get those ratings up and convince the advertisers that it's worth spending some money on Trekzone TV. All right, that's enough rambling from me. Thank you very much for enjoying this live part of today's proceedings. The 2023 Ningaloo Solar Eclipse Totality happened about 30 minutes ago. If you want to scrub back on Trekzone TV or our Facebook stream, you can do that. The DVR function is available. So scrub back about 32 minutes ago and catch that totality as I was bringing you the archive of Trekzone interviews, Talkin Science interviews. So yeah, get across that. Jump back about 32 minutes on the DVR function. That's why it's there. You can go back up to 12 hours on Trekzone TV on the YouTube and see what we've been doing. Catch up on a podcast that you might have missed. See what else the automation is doing. It's completely randomized. It's completely autonomous, which is just great. And the brilliant thing is I don't need massive amounts of server space to do this like you would have had to have done even 10 years ago. So that's absolutely fantastic. All right, well, it is time to wrap up the live component. Thank you very much for watching. This has been the 2023 Solar Eclipse from Trekzone TV on Facebook, on our YouTube stream as well. I'm Matt Miller, and this has been Talkin Science. I take you back now to the archive of Talkin Science.
Welcome to Talkin Science, where we dive into the latest news from space and science. The Australian Telescope Director of the Square Kilometre Array, Dr. Sarah Pearce, has beamed in. Dr. Pearce, thanks for your time.
Hi, Matt. Thank you very much for having me on.
Now, Dr. Pearce, what will the Telescope Director be responsible for?
Well, Matt, the Square Kilometre Array is a collaboration of 15 countries, and it's going to build 2 radio telescopes, the next generation of radio telescopes, the best in the world, be in South Africa, and then I will be director responsible for the one in Australia. And that's going to be what we call a low-frequency radio telescope. So it'll cover between 50 and 350 megahertz, for those of your listeners who are interested in such things. And it will be 130,000 antennas spread across the desert in Western Australia. And we're going to start building it towards the end of this year, maybe early next year.
Well, you've come from the acting chief scientist post of the CSIRO, where you were part of the astronomy and space science division. How have things changed there since the Australian Space Agency was formed?
Yeah, look, the formation of the Space Agency has been amazing in the way that it has encouraged and coordinated the space community across Australia. I have never seen any in the time that I have been in Australia in terms of the space sector. There's startups being formed, there's university groups focusing on space, there's industry playing roles in sort of national and international space activities. So the agency really has kind of catalyzed an enormous amount of work.
Now, you're familiar with the Square Kilometre Array already, I believe, having led the CSIRO's engagement in the international project. What will it be like to now move to the SKA full-time?
Yeah, look, it's an amazing opportunity. So as you say, as part of my role in CSIRO for the last 10 years, I've been helping to lead Australia's engagement in SKA, and I was one of the negotiating team who set up the SKA treaty between the countries who are going to build it. Now this is an opportunity to kind of really focus on this mega science project for Australia and really help deliver this, both for Australia, but also for the international astronomy community that will use the telescope.
I spoke with Curtin Uni's Nick Swainston a few weeks ago. He used data from the Murchison Wide Field Array to find a pulsar. Now, with that telescope array being the precursor to the Square Kilometre Array, what other discoveries are potentially on the horizon?
So, yeah, that was great work by Curtin to find that first low-frequency pulsar. So the real kind of core science goal of the low-frequency part of the Square Kilometre Array is to find what we call the dawn, or the epoch of reionization more technically. This is the time after the Big Bang when the first stars and galaxies started to shine in the sky. And there is no telescope yet that has been able to detect this. We hope that SKA will be able to detect it and possibly even image it for the first time in the world. So we'll find out much more about how those first stars and galaxies were formed and what that early universe looked like.
Now, as you said earlier, this is a multinational project with us taking the cake for the largest telescope of its kind, and we'll be hanging out in the lower frequencies. South Africa will be home to another array, and they'll be observing the higher frequencies. And the UK has the global headquarters. Are there challenges in working collaboratively across continents?
Look, I really enjoy this kind of international project, and the treaty negotiations that I were part of were really one of my career highlights because everybody is focused in the same direction. So everybody wants to build the best radio telescopes in the world. So it's a really great collaboration. The other good thing about working nationally, a country can bring their own kind of expertise. So the telescope will be built of parts constructed in different countries and then brought to Australia and South Africa and integrated. And so we have the countries like India who are working on the software, China who are building the dishes for the South African version of the telescope. And in Australia, we'll be doing things like building the infrastructure for the telescope and some of the really high-speed digital signal processing that will go into it. So bringing all that work together internationally so that that you've got really the very best of the world's radio astronomers and engineers working for the same project is really very exciting.
And I guess that's one thing to not forget as well in this project, that even though South Africa and Australia have the telescope arrays on the ground, there's many more countries involved in this collaboration to better understand the early universe.
Yeah, that's right. Look, we have many of the world's largest astronomy kind of countries engaged, and more becoming more engaged all the time. So since I've been involved in the project, it's gone up, and now we've got kind of 15 or 16 countries who are interested in being involved. And so, it brings its own challenges, of course, and being in Australia, time zones are perhaps our key challenge, and finding times to have meetings when everybody from Canada through Europe, through India, China, and Australia can all join in can be difficult. But I find it really energizing to be involved in projects of this kind of scale. And it's the first time Australia will have hosted one of these international mega science projects. So it's a great opportunity for us.
Well, there's going to be 131,000 dipole antennas in Western Australia alone, looking like Christmas trees, I believe. How exactly do they gather radio waves?
Yeah, so it's a bit like, say, your TV antenna. So they can pick up the radio waves like your TV antenna does, but they're very, very faint, what we're trying to listen to. And so we need to amplify the signals, and then because we've got 130,000 antennas, we need to join them all together in different ways, depending on what we're looking for. Why do we need so many antennas? Well, because we need high sensitivity. So you can't see what we're looking for with just one of these. You couldn't see it with your TV antenna. But we also need them spread out. So they'll be spread across 60 kilometres of the desert in Western Australia in order to give us really fine resolution. So the further apart things are spread, the more detail you can see. But the more antennas you've got, the fainter things you can see. And so that's why we've got such a lot and so spread out.
And the best part about the Murchison area of Western Australia is that it's really radio quiet, which is why the wide field array has been so successful. Now moving into the square kilometre array, that radio dead silence is key.
Yes, so absolutely. Because what we are trying to detect is so quiet, we really need to go where there's no interference. And although in the past you might have been able to build radio telescopes just on the outside of Sydney, which was where some of the first ones in Australia were built, now there are way too many people and we have way too many things that cause interference. So almost every kind of electronics that you use, from your mobile phone, your computer, your car, it all causes radio interference. So we need to go where there are very few people. And that's why our telescope will be built in the Murchison, around 350 kilometres from Geraldton, which is the nearest city. And similarly, the South African telescope will be in the Karoo, which is also a remote area of South Africa.
And it is going to be very, very exciting. I guess from a very early stage, it's been in development and the ideas have been floating for many years. Now we're moving into this construction phase. What's the energy like now with the Square Kilometre Array project?
Yeah, it's great. In fact, just recently in Australia, we've put out the first call for industry to be involved in building things as part of the Square Kilometre Array. I've been involved for 10 years in SKA, and there's people who've been involved for a long time before that. So it's fantastic to finally be at the stage where we have countries committed, and we've got the telescope design ready, and we're really getting now ready, just putting the finishing touches on so that we'll be ready to start building towards the end of this year or early next year, as I say. So that's going to be a great day when we kind of have shovels in the ground.
Well, jumping ahead a little bit, I cannot wait until construction is complete. Observing begins at that stage. Plenty of fascinating things out there to learn, I'm sure. Dr. Pearce, thanks for beaming into the Talkin Science and good luck in your new role.
Thank you very much. It was great to talk to you.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favourite podcast app 5 days a week. Just search for Trekzone and subscribe.
Welcome to Talkin Science. Professor Deanne Fisher is here to discuss galactic exhaust, the byproducts of stellar production. Professor, thanks for your time.
Oh, thank you for having me.
This is Trekzone's Talkin Science. And you can get exclusive behind-the-scenes info and first play access to all Trekzone podcasts by becoming a member today. Click join on every Trekzone video on YouTube. Go to thetrek.zone/support or scan the QR code on screen throughout the show. Now, it's back to you, Matt.
Well, thank you very much, Ross. And a quick mention of our socials. Trekzone's on YouTube, Twitter, Facebook, Instagram, and your favourite podcast feed. Find us, like, follow, and subscribe. Leave comments and ratings. That'll help us convince the algorithms we're worth it. Well, Professor, what goes in must come out. But it turns out in the case of your research, we have clean elements becoming dirty ones. How does that work and what does it mean?
Well, the way it works is that, so it starts very early in the formation of the universe. The universe made a very clean system, mostly hydrogen and helium. And then over the course, stars started to form. And when a star forms, it turns that hydrogen and helium into heavier elements, carbon, nitrogen, oxygen, all the way up to iron, and everything that you're made of, everything that you see around you came from a star. And so that's what we astronomers call polluting the cosmos. And that happens in galaxies where you have this clean gas from the universe, initially from the Big Bang, accreting, falling onto galaxies. And then galaxies, they swirl it around and crunch it into stars. And then a few million years later, those stars explode and they shoot the gas back out of the top of the galaxy in polluting the cosmos even more. And so it's a constant cycle. And what it means is it means that galaxies refresh themselves, and over time they change the universe around them. They're not isolated, they're connected to the part of the universe that they live in.
Well, when we say exhaust, I think of what comes out of the tailpipe of a car. Is what we have here as toxic as that on a universal scale?
Not at all. It's quite the opposite. So everything that you see is that exhaust. So what comes out of the tailpipe of a car is quite bad for you. But part of the exhaust from a star exploding is the atoms that make you up, that made up the planets that we live on. And so even though it's polluting in terms of what an astronomer says, it's actually quite necessary and useful for promoting life and eventually creating new planets around new stars in other galaxies.
Well, until now, we've only been able to guess at what happens in a stellar nursery, but this new imaging system that you and Dr. Alex Cameron and an international team used has certainly peeled back the curtain, hasn't it?
Yes. A few years ago, there was a sort of technological development for a way to make a new imaging system that can basically trick the light a little bit and allows us to see fainter than we could before. Now, if you take something that can see faint and then put it on the biggest telescope you have, and then sit on it for a really long amount of time, you can see really, really faint things. I really like to do projects like that, where we essentially do something that was completely impossible a year ago, but now because we're pushing on technology as hard as we can, that we can do brand new science and move into a new area. In this case, it was what's called the Cosmic Web Imager on the Keck telescope, which is located at about 4,000 meters in the sky on a mountain in Hawaii, which is a pretty great place to put a telescope.
I love the Keck Observatory there in Hawaii. And as you say, it gets it a little higher into the atmosphere, not making it as thick to see through to the universe around us. Now, the Keck Observatory did appear at galaxy MRK 1486, which is around 500 light years away. What made that galaxy a valuable target for study?
It's 500 million light years away. And what made it really useful was that it is it's in the act of forming tons of stars. So all these processes of gas coming in, exploding and shooting out are all kind of ramped up. So our Milky Way is a really big galaxy that makes about one new star a year, which is it's good. We don't want all that activity going on around us. We want a calm galaxy to live in. But that means we can't study these processes of stars exploding in as much detail because they're rare in the Milky Way. But in Markarian 1486, it is all these processes ramped up. And so the gas shooting up is much easier to see than it would be in a passive galaxy. And it also means that that gas has fuel, so the gas coming in is also more extreme. And so all these processes are turned up all the way so that we can study them in better detail.
And it's also edge on to us as well, making it a little easier to make these observations.
Yes, that's true too. Because it's so galaxies are just randomly aligned towards us. But if you want to see the stuff that's shooting above the plane of the galaxy, if a galaxy is kind of shaped like a frisbee or a plate or something, if you're looking at it on its side, you can easily see the stuff that is above where the rest of the material is. And that's what we want to capture with CAC. That's what we want to see and measure, which is what we did in this paper.
Now, one thing that I didn't actually mention at the start of the show is what elements we're talking about. So obviously hydrogen and helium being the easiest elements in the universe are what go in. What comes out? And are there other things as well that go in?
What goes in will change from galaxy to galaxy based on the chemistry of that galaxy, but it is mostly hydrogen and helium. And then what we are interested in is how much processing that galaxy did and how much processing. So in the core of a star, in the sun, in any star, you have atoms running into each other, hydrogen atoms running into each other, fusing and causing larger atoms, and eventually leading to carbon, nitrogen, and oxygen. And so we can use the ratio, the fraction of oxygen molecule or atoms to hydrogen atoms, and that ratio tells us how much processing is going on. And we call that, astronomers, everything bigger than hydrogen is a metal to an astronomer. We call that the metals. And so that ratio of heavy elements to hydrogen tells us how much evolution has happened. So we measured an emission line of oxygen directly, and then we also have the amount of hydrogen we have, and then we put those together for this measurement. And it tells us how much chemical evolution has occurred and how many stars have exploded and shot their material up into the universe.
And I think what's incredible with this research as well is that we're not hands-on with this material. It's analysing the data and the spectrums that come back to you from those observations. Obviously, a lot of training and a lot of skill goes into that, but what does that data look like when it comes back from Keck?
Well, there's a lot of processes that go through getting a photon from the sky into me calling it this amount of oxygen. We get first, you have to, of course, with the data, you have to remove things like the sky itself, features from the telescope itself. All of these things you have to very carefully calibrate out and remove from your data. And then after we process that through, we're left with what we call a data cube. And this is kind of a new thing in astronomy. It's a few years old now, but it's an image, but at every single pixel in your image, like you would have in your camera, you're basically looking at an entire spectrum of light where you have 100 or 1,000 values ranging based on the wavelength. And so you have a spectrum where each little position represents wavelength, and we have that for every image in a galaxy. And this is, so you end up with data sets that are, an individual image that we work with is something like 3 gigabytes alone. And then you have to process the whole thing through your computer. So at Swinburne, we have a supercomputer that we use to process data. And it's all a quite intensive project, and it requires a lot of graduate students writing lots of Python code.
Fantastic. Well, you were also joined, as I mentioned before, by joined in the research by scientists in the US and Chile as well. What's it like to collaborate on research with international partners?
It's a lot of fun. So I am not from Australia. I went to school in the US, and I basically, when I create collaborations, so this project is part of an ongoing long collaboration of about 10 professors around the world. And I basically look to work with my friends who are around the world. During normal times, we see each other a couple times a year. And we're all excited around the same topic. And the idiosyncrasies of waking up really early in the morning in Australia to talk to somebody in North America at a reasonable time can be challenging. But otherwise, people who do astronomy usually really, really love it. And so when you're working with somebody who's your friend, who's also really interested in what you want to do, and also they really love what they're doing, it's just a lot of fun. It's a fun job to have.
Very, very cool. Well, Trekzone membership costs less than a cup of coffee a month. It's available via the join button below on YouTube. For our podcast listeners, jump onto the trek.zone/support. Supporting me grow this channel gets you first play access and behind-the-scenes goss. Do it today. Have my eternal gratitude. Professor, thanks for beaming in for this edition of Talkin' Science.
Thank you very much for having me. It was a lot of fun.
Welcome to Talkin' Science Interviews. Matt Miller with you in Studio 4. Well, I'm very excited to continue this dive into the movers and shakers of science and space news that we're featuring on Talkin' Science on Tuesdays with Dr. Brad. Today, Dr. Matt Owers from Macquarie University is going to join me to chat about the SAMI survey that was released a couple of weeks ago.
On Apple Podcast, Spotify, Google Podcasts, and YouTube for over 550 episodes. This is Talkin' Science.
And Dr. Owers is joining me now from Macquarie University. Dr. Owers, thanks for a little bit of your time on today's Talkin' Science Interviews.
No worries. Thanks for having me.
Now, can you tell us a little bit about the SAMI Galaxy Survey? It started 7 years ago. What was the genesis of the idea?
Yeah, so actually it started back in 2013. And I guess the genesis of the idea is that we really wanted to understand why galaxies look the way they do. It seems like a pretty simple question, but actually it's really hard to answer. And so we had a number of ideas about how what galaxies look like. For example, we've all seen images of galaxies from the Hubble Space Telescope and other telescopes like that. And they all seem to appear pretty diverse. So we see a number of different shapes of galaxies. They have a number of different colours. So they can be blue or red. When we see very blue galaxies, that means they're actively forming new stars, for example. Or if we see very red galaxies, that means they haven't formed stars generally for a few billion years or so. So there's a diversity of characteristics that galaxies have, and our survey was all about trying to disentangle what causes that diversity. So in order to do that, we needed to use about 250 nights on the telescope with an instrument called SAMI, the Sydney AAO Multi-Integral Field Spectrograph. We like our acronyms in astronomy, as you might be fully aware.
Yep.
So SAMI it allows us to take what's called integral field spectroscopy. Now, integral field spectroscopy is essentially we take an image of a galaxy, but for each point in the galaxy, we have a spectrum. So a spectrum, you might be aware, is where we break the components of the light up into its different wavelengths, much like a rainbow breaks up the light from the sun into its different colours, but much more granular. And so that allows us to make many different measurements of galaxies and try and disentangle the diversity of the galaxies.
Now, some info has already been released over the 7 years of the study, which has led to dozens of papers. The release a couple of weeks ago was the third and final data set. What's it like to reach this point after such a long time with the Siding Springs telescope, with SAMI, doing all of this analysis, as you say, over 250 nights on the telescope? That's almost a full year just in and of itself. So to finally see the end of it, how is that feeling?
Relief. It's a hell of a lot of work, as you pointed out. Just the nights on the telescope alone almost adds up to a year, but there's a huge amount of work that goes into analysing the data. Well, first of all, preparing for the survey itself. So the target selection to understand which galaxies that we want to look at, there's a lot of preparation work that needs to go in there. And our survey built off of a pre-existing survey called the Galaxy and Mass Assembly Survey, which is also an Australian-led survey conducted at the Anglo-Australian Telescope in Siding Spring. And that had 300-odd nights on the telescope previous to our starting of the SAMI Galaxy survey. So on the shoulders of giants we stood and selected our targets. And that in itself took, we were doing that a year in advance easily of starting the survey. And then we start to talk about, analysing the data, making sure that we're not we haven't got spurious artifacts in our data, and also analysing our data to sort of bring out the science is a huge investment of time across many different astronomers within Australia and also overseas. So I guess relief at that coming to an end, but also a bit of excitement because now we're moving into a space where we can start looking forward to the next big thing in terms of what we're going to do with the Anglo-Australian telescope.
And I'm going to dive into that in a second. But with Sammy, all of these nights, all of this data, it was analysing 13 galaxies at a time. I can only imagine the amount of raw data that you are confronted with as the analysis begins and gets underway. How do you make sense of all of that sitting in front of you?
Yeah, so that was a good problem to have. Having a lot of data is an excellent problem to have, but it was also a new problem because the 3,000 galaxies we had, each of those had its own sort of IF integral field spectroscopy data, which itself contains something like 1,000 spectra per galaxy.
Oh, right? Wow.
And each of those spectra contains, almost 4,000 points of data. And so there's a huge amount of data to analyse there. And it's sort of it was a new realm for us to analyse that amount of data because previously we're used to having large surveys of several 100,000 galaxies even. But then we only have one spectrum per galaxy to analyse. So it's not easy, but it's easier to interpret the data because, it just led to a whole new level of complexity that we had to deal with. We didn't just have one data point per galaxy anymore. We had several thousand. And so, it was an embarrassment of riches to deal with. But you do need quite strong computational skills and computational power to do this in a human lifetime scale to analyse your data. Otherwise, if you're using computers from the 90s, we would never get through it.
Were there any surprises that came up in all the studies?
There were a few nice surprises. So I guess I'm completely biased. I'm going to talk about the stuff that I was surprised by.
Fair enough.
Previously, I mentioned that we had several other surveys previous to this where we had several 100,000 spectra of galaxies. So generally those spectra came from very central regions of galaxies. And so they told us about what's happening in the middle of a galaxy and didn't tell us much about what's happening in the outer regions. So, for example, if we were, several thousand or several million light years away and turn around and look back at the Milky Way galaxy with one of these surveys, we basically take a spectrum from the very central part of our galaxy that contains, a supermassive black hole and a spheroidal distribution of stars. But we wouldn't get any information about where we are as the sun in our solar system, sort of 8 kiloparsecs away from the centre of the Milky Way. So basically we received no information about that. So one of the things that I was interested in is looking at what the external parts of galaxies look like and how the external environment, we call it, influences the star formation, the formation of new stars in those outer parts. And what I was able to find is that when a galaxy zooms through a very dense region called a cluster of galaxies, where you have this sort of tenuous 10 million degree gas that permeates the space between the galaxies, what happens is a galaxy feels a wind, right? So it's like if you stick your head out the window of a car going at 100 kilometres an hour, don't do that, you feel a wind, right? It's all the air rushing past you. So a galaxy zooming through intergalactic space at sort of 10 million kilometres an hour also feels a wind because of this very hot gas. And it feels such a strong wind that it strips out any gas that galaxy might have.
Oh, wow.
And now what that gas in a galaxy normally does is it collapses and forms new stars. So once you take all that away, you stop the ability for a galaxy to form stars. And so what we were able to find was evidence for these galaxies that had recently fallen into a big, massive, sort of 1,000 trillion times the mass of the sun cluster of galaxies. And this interaction with the surrounding environment had stripped off the gas and stopped star formation there in the last billion years or so. So that tells us something about how the external environment influences how the galaxy produces new stars.
It is absolutely fascinating. I think the best thing that I love as a bit of a facilitator for science podcasts, I don't have a massive background, or I don't have a background in researching this sort of stuff. Hearing from researchers and professors and everyone in the field about the amazing discoveries that come up with these galaxies, and how there's still so many things to be discovered, and even after Sammy, there's still so much that can be learnt by galaxies. This isn't the be-all and end-all survey.
Absolutely, yeah. I think one of the amazing things that you may not often think about unless you're deeply embedded within this field is that galaxies change with time. I mean, it seems counterintuitive, like on the timescales that we are used to, sort of year-long timescales, galaxies don't change very much. But when you look at them in the context of the timescales that operate in the universe, a billion years is, not... It's a 13th of the age of the universe, but this is the sort of timescale that galaxies change on. And that's relatively fast.
And next up from Sammy comes Hector, who is planning to do even bigger things with galaxies. Brad and I were talking about this a couple of weeks ago, that Hector is basically the equivalent of hold my beer.
Yeah. So Hector, we've doubled the number of objects that we can, a little bit less than double the number of objects that we can observe at the same time to take this integral field spectroscopy with. And we've also doubled the breadth of the region that we're able to see. So with Sammy, I think our field of view was something like the size of the full moon. Now with Hector, we'll be able to double that angular extent. And so that allows us to probe many more galaxies at the same time across a larger area of the universe. And so we'll be collecting data for around about 15,000 galaxies for that survey.
That's incredible. That's over 4 times the amount of the SAMI survey. Are you ready for, say, 10 years? How much time is that going to take? Is that a 10-year, 15-year survey?
So we're hoping to be on Sky for about 5 years, and we're hoping to get a larger allocation of time from the telescope time assignment committee. So basically the way we get our time is we have to write a research proposal saying, what we want to do, what new things we're going to discover, and we have to lay out there how much time we want, which is sort of, we need to calculate that based off of what we want to do. And so we're hoping to get a large chunk of each year's worth of time over the course of 5 years to do our survey. And so again, I think it'll be something like a 200 or 300 night survey, a lot of observing.
That's actually something that I hadn't thought of. Obviously, not everyone has their own massive telescope in the backyard or on campus at universities. So there are a limited number of telescopes and many research projects to do. So it is a bit of a battle, I guess, or is it a bit of a battle to get time on the telescopes, get enough time that you need?
Absolutely. I mean, so the Anglo-Australian telescope, for a 4-metre telescope, it's quite competitive, and the reason behind that is because we have very good instruments on there. So we've, as an Australian community, we've been very good at inventing new instruments to use to make use of our 4-metre facility. And a 4-metre facility nowadays is not huge in terms of astronomy telescopes. We have 10-metre telescopes, the Keck telescopes in Hawaii, the very large telescopes in Chile are 8 metres. So, those telescopes are very competitive, but the AAT does very well. So I think that it's called the oversubscription. So how many applications go in compared to how many get awarded time, it's around about a factor of 2 or so for the Anglo-Australian telescope. So you need to write a good proposal, and it needs to be compelling scientifically, and it needs to be feasible. So it needs, they look at it and say, well, actually, can you do that? What they claim they're going to do with our telescope or not. And so you're judged based off of that and awarded time or not.
Fantastic, Dr. Owers. It is always fantastic to bring scientists onto Trekzone and hear about the stuff that is happening in the community, especially from an Australian perspective. I think the best thing that I've learned here at Trekzone is that we punch above our weight in the space and science communities, and Sammy and Hector are just further examples of that.
Very good. Thank you very much for your time, Matt.
This is Trekzone's Talkin' Science.
Welcome to Talkin' Science on location at the Whalers Way Orbital Launch Complex. Lloyd Damp is with me, CEO of Southern Launch even. Lloyd, I need to put the sunnies on because you're in person. This is very exciting.
No, thanks, Matt, and welcome to the site.
This is very, very exciting. The Southern Ocean is literally right there. There is a beach. Have you gone for a swim yet?
I actually haven't been for a swim this time, but I can tell you now, if that rocket flies nicely tomorrow,
naked run into the beach?
My bathers are packed, and we will be. I might take a dip in afterwards. That's for certain.
I love it, Lloyd. This has just been an incredible day here on the range. Being out, seeing all of this. We've talked about this over the years about you getting the license to be here, being out, developing this site, working with the local community. I was umming and ahhing about whether I was going to say anything. There obviously is some signage on the way in. There are some people that aren't happy that you're here. We've talked about this in the past, how you've engaged with the local community, you've engaged with the traditional owners, you've done all these things. I guess just as a stamp to give us, both sides of the coverage, what do you say to those people that don't want you here?
Our whole approach to developing the site has been very scientific, and we always are open to listen to people's points of view and have that scientific discussion around where we have a lot to learn. We're humble enough to believe that we've always got something to learn from people. So people come forward, we always love engaging with them. And of course there will be some that do not believe the science, and will come up with their own opinions, and that's fine. We don't all have to agree in this world.
Exactly right. And look, we've talked about how this is a very opportune site to get us into polar orbit. Australia's well positioned, good weather. Obviously, weather hasn't been terribly favourable here at the moment.
This year, it's snowing at the moment in Victoria. I mean, come on.
What is going on? Upper level winds delayed from today when we're recording. We're on tomorrow. I saw your face. I was very lucky to be standing next to you when you called out to all stations saying that we are go for launch. The smile on your face could not be wiped off by anything. What was that moment like for you?
Oh, mate, it's been years and years of effort to get us to this point. We've built a fantastic team. We've got a great customer in AT Space, and we've even got to the point where the T-Space, who came out back in September of last year, have developed a sister company that are going to be building this rocket and others here in Australia. So, this has been such a journey. We're not at the end yet. This is but step one.
But the beginning.
So, look, I'm wrapped.
It is awesome. Kestrel 1 standing behind us. It is the VSO2 mission. What's this first one going to be doing?
So this, one of the key things with any space launch vehicle is about in vacuum engine restart. So a lot of people potentially don't know this, but a rocket will never get you into a perfect circular orbit. So you get a bit of an elliptic orbit, and then you have to restart your upper stage engines to then circularize that orbit. So this flight will initially shut the second stage engine down early. It'll then coast for an extended period while it is in space, and then reignite that second engine. So it'll look a bit like a camel, two humps in the flight trajectory. as it then returns back to the Southern Ocean, there are grid fins and a parachute and other onboard systems that AT Space want to test out.
Very cool. So we're going to be doing a couple of orbits before we come back to the Southern Ocean, or we're up and down?
Up and down with this one. Even though this rocket is 10 meters tall, it actually doesn't have enough energy to get the payload section, so to speak, into orbit.
Right, and you're going to try and back this up with VSO3. I was talking to Shane just before, saying that there's the potential that you could turn around this site in 48 hours. It's only your third launch and you're trying to really just push things through. You really want to get stuff done by Christmas.
Well, so third from Whalers Way. We've done quite a few up at Kaniba as well. So from a team readiness perspective, we're very confident that we can have the range, wash, rinse, repeat type of activity. And I think it's testament to the professionalism of both us, our customer AT Space, as well as then all the different regulators who understand and appreciate the preparation that the teams are putting in to making this site safe and secure.
It was very interesting. I was chatting with the CASA representative, the Civil Aviation Safety Authority rep, who's here managing the airspace up to 10 kilometres, I believe it is. Could be a little bit more.
I think
whatever it is, it's up there. It's commercial aircraft.
Yes.
Looking at all of those, and it was interesting to learn as well something that I'm going to pursue on Talkin Science, because it's a side of rocket launches that I haven't even considered. Qantas and Virgin not terribly happy about needing to divert. To them, I say fiddlesticks and join the space age. I guess hearing about all the cooperation that goes into making this happen, all of the agencies, this is where we've talked about the Australian Space Agency, so critical for all of this.
Yep.
How easy does that make it for you? You don't have to contact Alan Joyce and Virgin and all these other guys to say, hey, I'm just going to put a rocket up.
I wish it was that simple, mate. So, for the last couple of months and weeks, increasing over time, we speak with all of the commercial airliners. We put in place, we tell them what we're doing. We work out protocols on how to communicate when temporary restricted airspace will go up, because it's very true that for an aircraft to divert, it's got to burn more fuel. It's got to take a longer path to get to where it needs to go. So we are very conscious of that, and so we try and time our temporary restricted airspaces such that they have the least likely effect on any commercial airliners. And then naturally, once the launch activity has finished for the day, we step down those temporary restricted airspaces as soon as possible.
Very cool. Lloyd, it is going to be absolutely fascinating. We are just under, probably from when I release this, going live now on Trekzone TV. We're 24/7, probably about 12 hours from the launch window. Right now, we're the last ones here. And so we're likely to be the last humans to see this rocket intact on this launch pad. Looking at that, thinking about the company that you've built and that you're in charge of, what are you feeling right now?
Oh, mate, I'm so proud. I'm so proud of the entire team and everyone who's come along with us, supported us on this journey. The biggest thing I keep telling everybody, even though Southern Launch is a relatively small company, we could not have got to where we are today without the incredible support, friends, families, other companies, people in government and international. So it's been a true journey of thousands of people to get us here. So a big thank you to all of those people out there.
And to your customers as well for entrusting you with their hardware and putting it up. Very, very exciting. Lloyd, good luck with the launch tomorrow. Good luck in the future. We're going to be back. This is the first in-person rocket launch for me. It's going to be exciting. Looking forward to it. I guess, is there a last word for you?
Oh, mate, I just wish it Godspeed and, fly out down that way.
Fly that way.
Out of the ocean and, we can be friends so long as it flies that way.
And just very quickly, I'm going to wrap it up, but it is coming back. So there's the secondary exclusion zone out in the Southern Ocean. There is going to be all reasonable attempts made to recover this rocket.
Not the second
stage.
The first
stage.
Yes.
Because where I'm going with this is, if they successfully recover a piece, is it going to be mounted and put in your office?
We haven't formally discussed this with AT Space, but I really would love for parts of any recovered portions of this rocket to go to, a place like the Space Discovery Centre, right, in Adelaide, as part of what's it called over in Questacon? Yeah,
yes.
In Canberra.
Yes.
So that other young people can see the great achievements of Australians and say, hey, when I grow up, I want to get into STEM, or I want to be involved in the space industry, right? Because you don't have to be a scientist or an engineer to be involved in STEM. The individuals that we have in Southern Launch and AT Space are boiler makers, fitter and turners, they metal fabricators, lots and lots of technicians and the like. So it's really exciting to be able to say to people, think of what you're doing. Maybe if you want, there is a role for that skill set in the space industry.
Well, that's an awesome answer and very selfless. So I love it. It is brilliant. Lloyd, good luck again for tomorrow. We'll probably be back chatting with you again once we've successfully put this one in orbit. We're going to turn around VSO3. So good luck with everything, and we will see you again real soon. Welcome to Talkin' Science. Dr. Benjamin Pope from the University of Queensland is here to discuss unexpected radio waves potentially coming from hidden planets. Ben, thanks for your time.
Well, thanks for having me.
This is Trekzone's Talkin' Science. And you can get exclusive behind-the-scenes info and first-play access to all Trekzone podcasts by becoming a member today. Click join on every Trekzone video on YouTube. Go to the trek.zone/support or scan the QR code on screen throughout the show. Now, it's back to you, Matt.
Well, thank you very much, Ross. And a quick mention of our socials. Trekzone's on YouTube, Twitter, Facebook, Instagram, and your favourite podcast feed. Find us, like, follow, and subscribe. Leave comments and ratings. It'll help us convince the almighty algorithm we're worth it. Ben, you and colleagues from the Netherlands have used their national observatory, Astron, to search for exoplanets, and it seems as though 19 red dwarfs are telling you a little more about themselves than expected.
Yes, no, we're super excited. So we used the world's most powerful radio telescope, LOFAR, to search the whole sky, or at least a large section of the sky, for radio waves from M dwarf stars, that is red dwarf stars, the smallest kind of star. And quite unexpectedly, we found many radio bright, but circularly polarized, that is, you pick them up with a circular antenna, radio sources. Now, what's quite exciting is this is exactly what Jupiter looks like if you look at it with radio glasses on. So radio telescopes looking at Jupiter see circularly polarized radiation from its interaction with its moon Io. Io is whipping around in Jupiter's magnetic field, and it's driving this powerful aurora that you see with optical light, but you also see powerful radio waves. And so we think what we're seeing is a scaled up version of the Jupiter-Io interaction around these other stars.
It is very exciting. And while we know that other planets here in our solar system emit radio waves as well, and that's their magnetic fields interacting with solar winds, this is the first time we've detected them from exoplanets.
Absolutely. This effect has been predicted for a very long time, but never yet been observed. And this is a really, exciting for two reasons. One is that we now have a new radio window to look for exoplanets. So everything so far has been done in the optical. Now we have radio astronomy can join the action. And with the square kilometre array coming up, of which LOFAR is a prototype, you'll get 10 times more sensitivity and a much wider field of view. So we expect to find hundreds of these. And the other really exciting thing is that these radio waves indicate that the star is interacting with its planet, and that this interaction could lead to radiation being dumped on the planet, which strips away its atmosphere and renders an otherwise habitable world uninhabitable.
Well, Ben, why were red dwarfs the focus of your study here?
Because they're very, very common, and they're very, very close, and they have a lot of planets that are very close into them, which means they actually have a very high probability of interacting magnetically. On the other hand, the sun, our planets are many times further away from the sun than these planets are from their star.
And one thing that I've noticed as I've been covering exoplanets here on Talkin Science over the last few months is that the understanding of exoplanets is gaining in leaps and bounds, is gaining momentum in leaps and bounds from these things that we postulated a couple of decades ago and didn't quite understand, to now finding them pretty regularly, and it becomes just a regular occurrence that, oh yes, we found another one. But this is certainly a unique way of doing it. As you say, radio astronomy can jump in on the action now that's been hogged by optical astronomy, and Absolutely. I guess makes it a little bit easier to find these planets in the comparison from radio to optical.
Well, I think it's less about it's going to be an easy way of finding planets, because even with the SKA, we're going to find hundreds, whereas tens of thousands of exoplanets are known thanks to surveys such as the Kepler Space Telescope. So it's not going to be a way of finding lots and lots and lots of planets, though we will find many, so much as in their physics. Being able to measure this magnetic connection between the star and the planet is actually, radio is the only way to do this. And this means it's a powerful new tool for understanding habitability. Lots of M dwarfs have these planets in short orbits. M dwarfs are faint, so these short orbits have Earth-like temperatures. But what if they're all scoured with intense radiation from their star? So these otherwise balmy rocks are actually uninhabitable and drenched in radiation.
And further study has ruled out planets bigger than Earth being around these red dwarfs. So if they're there, they have to be smaller. As you say, they're possibly being bombarded by radiation as well. So I guess another form of these exoplanets, another type of planetary body that's out there and doing its own thing.
Absolutely. Yeah, no, we'd love to be able to actually confirm these with other methods. I've spent a lot of telescope time trying to chase it down, and the best we've got is about 1.2 times the mass of the Earth as an upper limit. But there's plenty of, we wouldn't detect the Earth, and we think that this radio signal is consistent with something about the mass of the Earth.
It is very exciting research. Looking forward to hopefully getting some more data on these red dwarfs, focusing in on your attention. Ben, thanks for beaming in on this edition of Talkin Science.
Thanks. Have a good day, mate.
Stars aren't just inhabiting our universe. It turns out they're major contributors to it, from hydrogen and helium produced in the Big Bang to all of the heavier elements produced by stars. 2 new papers published this month shed light on how the youngest generation of stars will stop contributing those heavy elements to the universe within their lifetime.
This is Trekzone's Talkin Science.
My name is Julia Chinkograna. I'm a PhD student at Monash University in stellar astrophysics. So I study the chemistry of stars.
Very, very cool. Julia, welcome to the show. Now, as I understand it, stars are pretty important in building up the universe. Essentially, they're giant factories.
Yeah, absolutely. So if we go way back in time, we know that at the time of the Big Bang, we had hydrogen and helium produced, but everything else on the periodic table has been created after the Big Bang in stars, by stars, around stars.
Well, it's a concept to get your head around. These super hot stars spitting out elements from gas through their sheer power and that nuclear fusion that is well known amongst the scientific community. How does it all sort of work? They're created from hydrogen and helium, and they come up with all these heavy elements.
Yes, it's a really good question. I'll start by specifying that I look at low and intermediate mass stars. So stars like our sun that aren't massive explode as supernovae. So I think it's much more intuitive with massive stars because you can picture supernova explosion, the gas gets spurted out of space. But with stars that can't explode as supernovae, they go through a little bit of a different process. So stars like our sun at their lives will puff up into these big puffy giant stars. So you'll have the same inside, but their envelope will expand from, say, 1 arm of our sun to 200 times the radius that it is now. So they get this really, really low density envelope. And what happens then is that we have these things called stellar winds, and they start to slowly erode the outer layers of the star and chip away at that gas. And over time, they basically chip away at the whole envelope, and that gas is then contributed back to space. So anything that's in the envelope is contributed back to space. Everything that's in the core is locked away. So we're really interested in what kind of chemistry is going on and mixed into that envelope.
Now, the research you were a part of shows that even minuscule changes to the makeup of the star at its birth will fundamentally change what it produces through its lifetime.
We know that for nuclear reactions to occur, we need really high temperatures and really high densities. So that's in the very center of the star. But as I just said, everything that we do back to space has to be in that low density envelope. So we rely on this mixing process to mix created by fusion, by reactions, and mix those products into the envelope. The idea is that we found when you have higher initial metal content in the gas, it's that mixing process so that all the valuable metals and all the things they're really interested in are locked inside that white dwarf remnant, that core, and they're not mixed into the envelope, so they can't be contributed back to space. So the star can still undergo those reactions, but they're locked away and we don't get to see them recycled in the universe.
So if these stars are constantly adding elements to the universe, I guess then it's the next step to say that the universe is always changing and there could be new things, new elements for us to discover.
When you think about what an element actually is, so when we're talking about hydrogen has 1 proton and helium has 2 protons, I'm not sure about new elements, but what we're really interested in astronomy is thinking about, okay, we've got that big periodic table. Where are those elements actually coming from? It's not, that carbon only comes from this type of star and sodium only comes from this type of star. A lot of stars kind of overlap and make different contributions of each element. So there are particular really heavy elements that can only be formed in low and intermediate mass stars like our sun because they have such a long time scale. So they're formed by the slow neutron capture process. There are other elements that can only be created in really explosive events like supernovae. So it's kind of our project is figuring out where those all come from on the periodic table.
Now, your simulations showed that the high level of chemical enrichment caused the stars to act in a very unexpected way. What was that way?
What we already know about high metallicity stars is that they, because of how the elements interact in their gas, they're much puffier than a star with a lower metal content. So a low metallicity star is very compact and tight. A high metallicity star is puffier. So because it's more spread out, they have lower temperatures and lower luminosity, so power output. But what was really interesting is the impact of the higher metal content on the mixing processes that go in the center. Our study extended to a much higher metal content that has been published before. So we're looking at up to 10% metals, which doesn't sound like a lot, but the jump from say 8% to 10% is a huge one. And so our really exciting finding was that at such high metal thresholds, that mixing process is completely stopped. So what that means is that generally we'd have a star born with, say, 2% metals, and then over its lifetime it would undergo nuclear reactions, and we would expect that the gas that it contributes is of a higher metal content. So it produces fresh metals. But for our stars with really high initial content, they're not, the gas that they expel at the end is the same amount that they started with. So there's no net production of metals that they're expelling.
Now, one thing that always fascinates me with this, Julia, is just how you come up with this research and make these conclusions, because it's not a matter of visiting these stars and digging and exploring as you might say on Earth or something like that. It's looking at radio data and stuff like that and the wavelengths of light. I'm guessing, am I sort of in the ballpark here?
Yeah, you're right. It's we can't just go visit these places. We can't really experiment with them in laboratories. So it's important to point out that our work, myself and Amanda, is purely theoretical. So we might have an observational astronomer look up at a galaxy and say, oh, there's a ton of element X here. I wonder how that got there. And as theoretical astrophysicists, our job is to figure out the story of what happened to get to that much of element X in that galaxy or whichever situation you want. So we use a series of numerical simulations. We have a few differential equations which we know map how the physics works in stars, and then we iterate them, and they go on, and they map the evolution of the star. It's difficult though, because we can't necessarily check our results because there's, it's not that there's necessarily a right answer. It might be that element X is not just from this type of star, but it's from a few different contributions. So the best way that we have of checking that is that we've got an international field where people all over the world are using codes that are they use the same equations, but they're built differently, and they're built by different teams who have slightly different input physics and mathematics. So the hope is that you'll have 3 teams around the world using completely different codes who haven't necessarily spoken to each other, and then they all get findings that are relatively similar, and you keep iterating and building on that until you can agree. And then the best way after that is to get an observational astronomer to say, yep, I measured this, that's correct, I think this all fits, until 10 years later, then something, revolutionizes it, and you've all got to start from the start. But yeah, it's a process of iterating by different groups.
Well, we should mention Professor Amanda Karakas. She also had a study which was released as this month as well. So working together to study these metal-rich stars, what were sort of the differences between her research and yours?
So Amanda, our first paper was about purely the evolution of these stars. So using those differential equations and saying, okay, at the birth of the star, this is where the temperature, density, and pressure is. And then a million years later, this is where the temperature, density, and pressure is. And we basically quantify those variables over the evolution of the star. But to do that, we only need to follow a few basic nuclear reactions. So we follow the energy-producing ones, like hydrogen to helium and helium to carbon, because they produce the energy of the star. Then I can take her output, so the structure of that model, where those variables are at each time step, and I've extended the network to a series of 77 isotope species. So I'm following reactions that don't contribute a huge amount of energy to the star, but are interesting because of their nucleosynthesis purposes. So looking at where these elements come from. So the 2 papers build on each other. Amanda started the work with the evolution, and then I've extended the network to look specifically at the chemical contributions of the stars.
Eventually, these stars will expand to become red giants before collapsing on themselves as white dwarfs. At that point, they will become a vault with no further contributions to the universe. It's incredible to think that from hydrogen and helium, the most basic of elements, carbon, lead, and all manner of other elements can be produced. My thanks to Julia for beaming in today for this Talkin' Science edition.